Hello, folks. Okay, so this will be the Chapter 9 recording for the lecture. Please let me know, send in any questions if I don't cover anything enough for you or if you didn't understand something, okay? Alright. So this chapter we're going to be doing covalent bonding orbitals. This chapter actually largely builds off of Chapter 8. So if you're running into parts here that don't make any sense, you really need to go back and review Chapter 8, come back here to Chapter 9, and see what's going on, okay? And there's some review activities that I've put up, and I've even put up some videos on things like drawing Lewis structures for that. So this right here is going to be in every chapter, and you should just go ahead and get used to it. This is actually the sections in your book, so if you're looking for a specific topic, which these headers will be on all the slideshows, which section it's from, that's where you go back and read more to learn more about it. Alright, so section 9.1, this is going to be the hybridization and localized electron model. From now on, I'm not going to say that, it's just going to be there. And then you can go ahead and pause and look it up if you need. Remember, whenever you do a lecture, you really should at least skim through the book first and then do the lecture. Because I'm going to expect you to have some idea of the language, okay? If you have no idea at all what this language is because you didn't skim through and you didn't at least look at the bolded words to find out what they mean, you're probably going to end up getting stuck whenever I use a new word, even if I define it. And that's all you're going to get out of it, is the vocabulary. And that's less than 20% of the lecture. So it's much, much better if you always review the book before you try to do a lecture, okay? So hybridization, this is going to be the mixing of native atomic orbitals to form special orbitals for bonding. This is how we get those geometries that are not like the orbitals we've seen before. For example, the S's are spheres, that's easy, but the P's actually have 90-degree separations. You have an X, Y, and Z P orbitals. And that's why you have 6 electrons in the P block, which would be where you'd find things like carbon, fluoride, etc. Because again, if you don't remember, each orbital can hold up to 2 electrons. By the way, the s orbital block, which is where you'd find things like sodium, hydrogen, etc., they can only hold 2 electrons. That's why that block, if you look at that area where you find sodium, hydrogen, etc., only has 2 elements across, as in like that, groups 1 and 2. Alright, so for example, hybrid orbitals are going to be, hybridization is going to look like this, where you have an sp3 orbitals. Now, this is actually much, much, much easier than you probably think. So right now, coming into this, everybody always thinks this is going to be extremely hard, and so they try to enter this thinking, I can't understand this little language right here, this doesn't make any sense, blah, 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 and they make it harder than it needs to be. So when you're looking at these, there's one really important factor that you should remember about orbitals, and that is that you can't create something from nothing, okay? All matter, all energy is neither created nor destroyed, right? You only can recycle it. You can only change its form. And so that's true about orbitals as well. So when we look at this sp3 orbitals, well, we have to have the same number of orbitals coming out as we do coming in, all the time, always. So what that means is that these sp3 orbitals, it's going to be a series of 4 orbitals that we're going to form using one s orbital right here, and then 3 p orbitals. Well, that tells you a lot. That tells you that you have an S going in and then 3 P's going in. Notice that's a total of 4 orbitals going in. And so the number of orbitals you have to get out of this is the same, 4. You can't get any other. You have to get the same number all the time. You cannot ever create or destroy energy, matter, nothing. Okay? So, you'll notice that is a central tenet of modern sciences, period. Doesn't matter what science you go to. So, keep that in mind. This should always be something that's always in the back of your head anytime you think of modern day anything, okay? Now, this sp3 orbitals, well, that also tells you something else. You notice that I've said that every orbital can have up to 2 electrons in it. Well, that means that since you have 4 orbitals here, you can have up to, well, 4 times 2 is 8 electrons in these. You cannot have more, you cannot have less. You can have less, that would mean it's not filled, okay? But you cannot fill it with more electrons, there simply isn't space. The example I always like to use for orbitals is your desks. So everybody sat at desks before and they have space for, say, 2 people in them, okay? Well, you can't add a third person in there and expect it to be stable. It's going to become unstable, which means people can't take notes anymore, right? And so in these orbitals, you cannot have more than 2 electrons in there without it and it be stable. It would eject the other electron if you try to put one in. So atoms that undergo this process are going to be said to be sp3 hybridized. What that means is that their s and p orbitals have mixed together in their valence shell. These mixed orbitals are going to be what we call hybridized orbitals, and that's your language right there. You can think of it a bit like making a Liger. You have an S and a P, and they make your hybrid. Now, sp3 hybridization of a carbon atom here is going to show you our nice tetrahedral arrangement. This actually solves something that you may have picked up on if you remember chapter 8. And that's that tetrahedral shape that we were talking about in chapter 8, that is that sort of camera stand shape or pyramid shape. I like to say it's like a camera stand. It has the 3 legs coming down, and then you have the arm going up to hold the camera. And so, like a camera stand, right? But that is called a tetrahedral arrangement. You may have noticed that these single bonds, these should have been overlaps of orbitals to hold electrons in them, because again, orbitals are where electrons can occupy. And so this didn't make sense, this shape, if you had p orbitals. It just can't happen, because see how these p orbitals are pointing in the x, y, and z direction? That's not the x, y, and z directions. This is something different. So what this does is it mixes these 4 orbitals, these atomic orbitals, in a hybridization. This hybridization actually gives you the largest separation of distance between each of these groups of electrons, or these orbitals that will have electrons in them. Why does it do that? Because this is going to be the lowest energy state. Think of it a bit like this. Now, if I ask you guys to all go into a classroom, we're not doing classrooms right now, but if I asked you guys to go in a classroom, would you guys all try to sit at the same desk and have 20 people all stacked on the same chairs? No, because you repel each other. You don't want to be so close to each other. What you will do, though, is spread out sort of the maximum distance possible in different groups, and that's because you want a little bit of buffer zone between your different social groups. In electrons, again, we have repulsions between 2 electrons. They're going to separate as much as possible, and so you're going to get this maximum separation between electrons. And that's what we have in these hybridization orbitals. Now, right here is the orbital energy level diagram. You may remember these orbital energy level diagrams a little bit. They're going to become a little bit more complicated, but really just more explanatory. Okay, they're going to actually start making some sort of sense now. Whereas before, it was just this abstract thing that really didn't tie much into anything. So these orbital energy level diagrams, when we look at them, they always have from lowest to highest energy. So the stuff on the bottom is the lowest energy. The stuff up above it is higher energy and higher energy and higher energy. Now, right here you'll see that we have a 2s orbital. What does that mean? Well, this means that this is a sphere shape, which was what the s orbitals are. This one is on energy level 2. Now, if you remember, your energy levels correspond to your periods, okay? So, for example, if we were to go down the periods on the periodic table, hydrogen has a 1s orbital. That's where its single electron is located. And so that is the tightest, closest to the nucleus. If we go down the periodic table to below that, we're going to start seeing a 2s orbital come about. That 2s orbital is around the 1s orbital. It's further out, okay? Like a little nesting doll shells, we have the 1s inside the 2s. The 3s will be beyond that, and the 4s will encapsulate all those. And so these are going to be higher and higher energy as you go from 1s to 2s to 3s. Now, we can write out these interorbital energy level diagrams where they would have every orbital you could possibly account for. The problem is we don't need all of those. So, when you talk about things, you only talk about the valence shell usually. We can safely ignore everything but the valence shell because those are very, very tightly bound. Much like when you're talking about the money you spent, it isn't the value in your textbooks. That's not your money you're talking about, right? Or, for example, if you're talking about, man, I scraped myself. Well, you're not talking about your intestines, are you? Because that's inside, that's encapsulated, that's the stuff inside. You're always talking about the stuff outside because that's the ones that interact. And in the case of an atom, that's going to be your valence shells. So, right here, when we look at this, we have a 2s orbital and a 2p orbital. By the way, if you're curious, chapter 9 is always the longest chapter. None of the other ones will ever be these long because I always have to do a little review in this. You can notice I've always had going back into chapter 8 stuff, which theoretically you should know. All right, so when we look at this 2s and 2p orbitals, again, there's only a single 2s orbital because that is a sphere. There isn't any difference in directions. There is 3 2p orbitals. Those would be the x, y, and z. You will notice that they don't have any difference in energy. You see that? And these are called degenerate. That means that they have the same energies. 2p orbitals all have the same energy here. They are degenerate. The 2s orbital has a different energy that is not degenerate with the 2p orbital. Okay, so this means that you would have a very low energy electrons and higher energy electrons. So what happens is you have hybridization. This is going to mix these orbitals. These mixed orbitals are going to sort of average these energies. And these should be a little bit lower on average than these orbitals here. And so this is going to give you your hybridized orbitals that you would have in something, say, like methane. These are the orbitals that are going to make those single bonds from C to hydrogen. These are the carbon ones. All right, so these are your sp3 hybridized orbitals. You will notice that these sp3 hybridized orbitals, these are degenerate. These are all going to be degenerate, and that means that each of these bonds is the same energy because it's in the same energy orbital, etc. All right, so whenever an atom requires a set of equivalent tetrahedral atomic orbitals, this model is going to assume that the atom adopts a set of sp3 orbitals. And remember, this is going to be a theory. If you don't remember the difference between a theory and a law, well, laws are what we observe, okay? They just are what we observe. They don't explain it why. They don't explain anything about it. They can be tested every single day by everyone on the planet because that's what a law is. It's just what's happening. A theory is going to explain why things happen. And theories can never truly be proved. They can only repeatedly be attempted to be disproved. And when they stick around for long enough, we begrudgingly go, maybe. Okay? Now, when you want this set of 4 orbitals are going to be in bonds, you're going to hold electrons in them, this atom will undergo sp3 hybridization. And that is what your sp3 hybridization that you've seen so far is doing. It's making 4 equivalent orbitals that are going, none of them are going to be particularly higher or lower energy, around this carbon, and those are your sp3 orbitals. There we go. Remember, sp3, how can you tell how many orbitals or directions you would have electrons contained in? Well, that is 1s and then 3p orbitals. That means you have to have 4 different directions electrons are contained in. Okay? So what if your sp3 hybrid orbitals, excuse me, I guess I need more water, were higher in energy than the p orbitals in your free atom? How would this affect our model of bonding? So what would happen if instead of being lower in energy, these were actually higher in energy? Well, think of orbitals like a jar, okay? When you throw peanuts or jelly beans, let's use jelly beans, that's more colorful. If you throw jelly beans into a jar, they settle to the bottom first, right? Doesn't matter what the shape of the jar is, it's jelly beans are going to go to the bottom because that's the lowest energy. And then they will slowly stack up because they repel each other, actually due to the electrons in the outer surface, if you're curious. That's why things don't merge together. They will actually stack up and they will get higher and higher in the jar, right? Because that's higher and higher energy. So what happens if instead of being lower energy, this would be higher energy? Well, that means it wouldn't fill up. So what you would get instead is you would actually have your hybrid orbitals not forming. They would instead just fill up the 2p and 2s orbitals. That would mean that CH4, for example, would not be tetrahedral. It would actually be sort of a strange 3-direction bonds, and then one probably popping off from the s orbital in whatever direction happens to make it most stable. It would be quite a different looking thing. You would have 3 of them very tight to each other, and then one very far away from the others. Because it would have nothing to do with a tetrahedral shape anymore, because it does not have a tetrahedral arrangement, which is our sp3 arrangement of our orbitals, like we're seeing right here. Because those would be higher energy, they would not fill up. Okay, describe the bonding in the ammonia molecule using localized electron model. Alright, so whenever we do questions, I would highly encourage you to go ahead and just pause and then attempt the question yourself. Give it a solid 5-10 minute attempt, okay? If you have no idea where to go, then just come on back, okay, and look at what I did. If you find out that you have a pretty good idea where to go, just try it, okay? Because this is going to vastly improve not only your understanding of this material, but will actually be how you build up critical thinking skills and your IQ. That's how you get smarter, okay? If you just follow along with whatever I say, you're not actually going to get smarter. You will slowly learn the material, slower than you would have if you did what I said here. But yeah, that's it. That's all you get. And that's the least of what you get from a college education. What you really want to get from a college education is in this order: the ability to study. Number 2 would be the ability to critically think and just solve problems on your own. And then the third is actually the material we're covering. That is the least important of those 3 things, if you're curious. All right, so let's go into the solution. First, I'm going to get a drink of water, though. All right, I'm back. Okay, so the solution to this, where we describe the bonding in the ammonia molecule, there's actually several parts to this solution. because for a complete description, we need to look at from several angles. Okay. We're going to use the localized electron model here. By the way, if you pay attention to chemistry vocabulary, the words themselves tell you a lot, because chemistry is a language that is very succinct. It means exactly what it says, no deviation whatsoever. So if you really pay attention, whenever I ask you things, I'm actually giving you a lot of information. All right, so a complete description of your bonding is going to be 3 steps. First, we need to write out the Lewis structure, because that's how the atoms are going to connect. Once we have our Lewis structure, then we can really start diving into the rest of it, like what sort of shape are these going to take on? And that's going to be determining arrangement of the electron pairs, so where those electron pairs are located, which the Lewis structure will actually show us, and our VSEPR model to see how they're distributed from each other, which is our 3-dimensional shape. And then the next thing is we'll finally determine the hybrid atomic orbitals that we need so that we can describe our actual bonding in our molecule. These things like the hybridization we just talked about. Okay? Now, keep in mind that when I do these in class, I'm going to do all these problems in far more detail than you would probably ever actually work them out, okay? I don't expect every single one of you to need to go through the steps and describe it's things like addition, subtraction, write out every single Lewis structure using the correct method of doing it, when you've probably seen dozens of them that are exactly like that. Okay? Once you've done a number of examples for these, you're probably going to find that you can do these much, much faster than I will do here, okay? At least you should. However, I'm going to do them in a fairly complete manner. So first we need to do the Lewis structure for NH3. Now, it looks like this, and what you should be doing here is, if you remember how to do Lewis structures, you should count up your number of valence electrons. You find those number of valence electrons from your periodic table. And so, for example, we would look at our periodic table, and hydrogen is in group 1, so that is 1 valence electron. And so each hydrogen would have 1 valence electron, so that would be 1, 2, 3 from NH3. Then we would look at N. We look at that on our periodic table, and we see that that is in group 5. And so group 5, that would mean 5 valence electrons. That means that we have a total number of valence electrons of 8. If you want a complete guide on how to do Lewis structures, by the way, I have made a number of videos where I have done various different types of Lewis structures using the method I prefer to do them with, which is a complete method where you cannot screw up. Okay? Okay, so we have our number of valence electrons. That is 8 electrons. Remember that we cannot create nor destroy, so that means we have to use 8 electrons in this Lewis structure. So the next thing we're going to do here is we're going to figure out what's in the middle. And what you always do to figure out what's in the middle is you always look at your periodic table and figure out what is the furthest from a noble. Okay? The thing that's furthest from a noble needs the most bonds, and that means it's likely the middle. It's the one in the middle. And so we can see that hydrogen is a single step from a noble gas, neon. Nitrogen, on the other hand, I'm sorry, not neon, helium. I jumped forward. Nitrogen, on the other hand, is 3 steps away, which means that nitrogen has to be in the middle. Okay, Lewis structures are always going to have bonds. And so what we do is, the first thing we do is we always write in the nitrogen symbol, which will be in the middle, the thing in the middle. We then make single bonds. That's these lines right here. Please do not use the 2 periods that you sometimes see in books and various guides. It will only cause you havoc and problems. Okay? Use the lines for bonds. It will keep you honest and it'll keep you on track. Alright, so you make these bonds to the rest of the atoms. So we have hydrogen bonded to nitrogen. hydrogen bonded to nitrogen, hydrogen bonded to nitrogen. Each of these bonds is always going to be 2 electrons. By the way, if you've been paying attention, you went ahead and thought about it a little bit instead of just sort of listening to me, which is always a great thing to do, you would realize right here that these are orbitals overlapping. That's what makes a bond. Why do we have 2 electrons in a bond? Well, that's because those overlapping orbitals can only hold 2 electrons. There you go. Look at that. That actually is logical sense why there's 2 electrons in a bond. Alright, so we made these 3 bonds. That's 6 electrons. We would have 2 electrons remaining from our valence electrons. And so what we do first is we look at the outer atoms. Hydrogen, hydrogen, hydrogen. And we look how many are associated with each of these. So this hydrogen has 2 electrons associated with it. That means that's full. That hydrogen has 2 electrons. That's full. Can't accept those lone pair, that extra 2 electrons. This right here is full because it has 2 electrons associated with it. On the other hand, now we go to the center after we've done all these surrounding atoms. And we go, well, nitrogen, this can have up to 8 electrons. How do I know how many electrons nitrogen and hydrogen can have? Well, I look at my periodic table. I look at how many steps it can go across. So hydrogen is on the first period. I can only have 2 elements on there. That means you can only go 1, 2 across. That's all you can hold. And that's because there's only an s orbital on that first period. That's it. Nitrogen, on the other hand, is on the second period. If you look at the second period, you have your s block, that groups 1 and 2. And those is 2 electrons. That's 2 spots, right? And that's because your s orbital is one of the orbitals you have on your second period or second energy level. Now, when you go across, you then see that there's another block on the second period or second energy level. Those are your p orbitals. And so those would be your 2, energy level 2, p orbitals. And there are 3 of those, x, y, and z, which is why there are 6 elements over on the right side of the periodic table if you just count across. There's 1, 2, 3, 4, 5, 6, right? And that means that nitrogen then can have 2 electrons in its s orbital, 2 electrons for each p orbital, and that is a total of 8 electrons. And so to be full, nitrogen needs 8 electrons. I'm trying to connect the dots here for you guys because this all actually sums up, and if you truly understand this, this actually wraps a nice bow on the entire first semester of chemistry, where you really will truly understand what the heck's going on and why things are doing what they are. All right, now, that means that nitrogen, which had 6 electrons associated with it from the 3 single bonds, that's 2 electrons in each single bond, so 6, would need 2 more electrons to be full. And so we can put our 2 remaining electrons from the valence electron number that we figured out before right here as a lone pair. That's what that's called. Notice it's out on its own, is a pair of electrons. This does not have another atom above it, and so that's called a lone pair. All right, so when we look at this, what do you notice? Well, if you look at this honestly, you'll notice that there is 1, 2, 3, 4 different areas, right, or groups. They're pointing in different directions, aren't they? I like to call these groups or domains. So I will call this an electron domain. Your book has there's a number of different vocabulary terms. Every single book has different ones. I do not like this book's version of it. It is not a good wording for it. And so I'm going to have you say electron domain with me. Please say that. And we'll go ahead and just move on, okay? Just realize your book's term is something I will not use because I just don't think it's a good terminology. It's bad. Okay, so this is an electron domain. By domain, what do I mean? It's an area that's controlled by these electrons. It's an area that no other electrons can go into reasonably well because they will be repelled. And so this is a domain where you have 2 electrons occupying. This would be another domain. This is another area that would repel this other domain. And so these are separate. They have separate directions or areas where they have control over, right? Which is why I use the word domain. So this right here is another electron domain, and this one would be another electron domain. They would all repel each other, and so they want to separate as much as possible. And so what we can say is that there are 4 electron domains. Those 4 electron domains are composed of 3 bonds. These would be a bonding electron domain. This would be another bonding electron domain. And finally, that is another bonding electron domain. This right here would be a lone pair, okay, or a lone pair electron domain if you want to go a lot of words that you don't really need to say. But this is a lone pair right here. You will notice that your electron domains will always be composed of your bonding domains and your lone pairs. And so when you add these together, they will give you your total number of electron domains, okay? Your bonding and your lone pairs added will give you that 4 here, which is your 4 electron domains. All right, now, and electron domains are always composed of bonding and non-bonding electron domains. Bonding electron domains, non-bonding electron domains, or lone pairs. Now, your book likes to say electron pairs. I'm going to use that language in the slideshow because I like for this to match up with your book as much as possible. But no, it is a kind of a bad language. Now, these electron domains, if you have 4 of them, to minimize the repulsion, the best arrangement you can do is a tetrahedral arrangement, okay? That's going to give you the maximum separation between each domain. And so this is going to be a tetrahedral arrangement. Now, it's funny that all books I've ever seen always do it in this exact order, which leads you, the students, to believe you must do it in this exact order, okay? But it is not actually true. Now, you don't actually have to figure out what the geometry of this is to figure out its hybridization. So I want you to take a step back here. Forget that this might be 3-dimensional and you might want to look at a picture of it or something, right? Just look at the number of separated domains, the number of separated areas. So if you have a hybrid orbital, that is one area that electrons can be in. That's what it is. That's what all orbitals are, okay? They are areas that you can contain electrons. That's it. That's all an orbital is. It's an area to put electrons, period. Where you'd find the electrons. Okay, all those things mean the same thing, and they're all true. Now, when you look at this, you can see that I have 1, 2, 3, 4 areas I'm trying to put my electrons. And so that means I need 4 different orbitals to put those electrons in. And so when you try to figure out hybridization, there's a very, very easy way to do it. Just count up your electron groups, 1, 2, 3, 4, and then you go, okay, I have 4. How do I get 4 different orbitals in a hybridization? Well, that would be an S, 1s, right? You have 1s. There's only 1s you can put in, so you just can do one of those. So S. And then I would need 3 p orbitals. That would give me 4 orbitals, hybrid orbitals, which would be 4 different domains. And so, because I have 4 here, 4 different domains, this has to be sp3 hybrid orbitals, period. Because I have 4 different areas I need to put electrons in. I need 4 different orbitals to contain those electrons. That's it. Okay? There isn't any other option there. All right, now, in our NH3 molecule, 3 of the sp3 orbitals are going to be used to bond our hydrogen atoms. And that's what we're looking at right here, right? These 3 bonds, those would be 3 of those orbitals. The last is going to be used to contain the lone pair. And that will be the last of your sp3 hybrid orbitals. Now, one of the common mistakes people make is thinking that when I say sp3 hybridized orbitals, that you can somehow both have sp3 hybridized orbitals and then somehow split out one of those orbitals. You can't, okay? Once you have an sp3 hybridized orbitals, that is sp3 hybridized orbitals. They are that, okay? They are not p orbitals anymore. They are not s orbitals. They are hybridized orbitals. That is it. You can't split them back out, okay? All right, so that's what this looks like. There's your three sp3 hybridized orbitals. Those are these little deals right here, lobes, if you will. And then you have your lone pair up here. Okay, so there's an sp3 hybridization going on. Well, that makes you and leads you into the fact that, hey, there's probably other hybridizations, isn't there? For example, there could be an sp2 hybridization. So you would combine an s orbital, and then you would combine two of the p orbitals. This leaves you one of the p orbitals that has not been combined. That is separate, that is not part of the sp2 hybridized orbitals. Okay? Now, three objects, maximum separation, would give you a triangle. And so this would give you your trigonal planar arrangement of your atomic orbitals. This would give you that 120 degree bond angles that you may have seen in chapter 8. You may remember. This would also give you a p orbital that is not being used. And this p orbital would be above and below the plane of that triangle. So that would be coming in and out of the triangle. Okay? And that would be called oriented perpendicular to the plane of your sp2 orbitals. By the way, many people end up asking me things like, why is this not py, px, why is it pz, that sort of thing. The x, y, and z, when you talk about chemistry and atoms and molecules, is actually entirely arbitrary. You literally just set it to whatever you want, okay? And what is normally done is that x and y are laid flat on the paper when you're talking about x and y. And that means that z then would be coming out towards you, okay? That's just because people are used to reading xy graphs, right? And so xy, flat on the paper, that makes sense. And then z comes out towards you. And that's why that's considered perpendicular here to your sp2 orbitals, which remember are a trigonal planar arrangement. That means a triangle that is in all one plane, like a flat triangle. All right, so this is your sp2 orbitals. This is a mixture between an s and two p orbitals. And so this is going to, again, give you that same lobe structure. I haven't mentioned this smaller lobe. We'll mention it in a bit, but right now you don't really need to worry about it, okay? All you need to worry about is how they come together. And so this sp2 hybrid orbitals, which there are, well, how many again? We look at this and we go, there's one s here, there's two p's, and so that means there are three total hybrid orbitals, which we see right here, 1, 2, 3. Remember, you cannot create nor destroy. And so when we stack all of these together to get maximum separation, we're going to give a triangle like so. All right, now this right here is going to be your orbital energy level diagram for your sp2 hybridization. And you can see again, these are going to merge. That is going to have these become degenerate hybrid orbitals, same energy. They will always be somewhere between the s and the p orbitals. The exact place these end up right here actually is very complicated, so we won't go into that, but they'll always be somewhere in between, okay? This right here then would be your p orbital. This was not used. This is not part of the hybridization, and so it stays pretty much the same. And so you have your p orbital there, alone by itself. And so this is how they all sum up. Right here is your sp2 orbitals, hybridized orbitals, And these hybrid orbitals are arranged in a triangle. And you can see that triangle right there, right? And that's the plane. This is then the perpendicular p orbital that is remaining. Remember, this can hold up to 2 electrons in this p orbital. That is, both lobes that are going up and down is a single p orbital that can hold up to 2 electrons. By the way, another false thing that students oftentimes jump ahead and try to think happens is electrons do not occupy these orbitals, 1 electron to each lobe of the orbital, okay? Don't get stuck in that false analogy. They really just pop in and out of these randomly. There isn't really an occupation going on there. In fact, this is just a likelihood of finding electrons in the area, okay? They are not containers that you line things up nicely in, but they're a very good analogy for you. Now, these are the types of the sp2 hybridized bonds that we can have. So before, where we talked about sp3 hybridized orbitals, well, those can only make straight overlaps. They don't have areas to the side that can easily make other types of overlaps. When we get into the sp2 hybridized bonds, the bonds made using sp2 hybridized orbitals, we have 2 options, and that's a sigma and a pi bond. So sigma bonds are going to be an electron pair is shared in an area centered on a line running between the atoms. So the electrons will be located somewhere between those 2 atoms being shared by those 2 nuclei, okay? And that's what you've been thinking of the entire time you've been doing all these single bonds, is a sigma bond. And it's kind of easy to remember too, because sigma, single, bond. Okay, so that's directly sharing the electrons. By the way, that is the only type of bond in an sp3 hybridized atom. That's the only type possible even in an sp3 hybridized. Now, in the sp2 hybridized orbitals, you will notice that we did not use one of the p orbitals. And this p orbital can actually do what's called overlap on the side to another p orbital. So if you get 2 p orbitals next to each other, the sides of those p orbitals can overlap, and they can share electrons between them above and below the plane of the atom. So sort of passing along to the side, right? And so parallel p orbitals can share electron pairs, which then occupies the space above and below the line joining the atoms. And so when we talked about those double and triple bonds, well, if you thought a little bit, then they didn't make sense without this, did they? So a single bond is direct overlap, right? But once you have a single bond, you can't fit any more electrons directly in between those 2 atoms. They would repel. They wouldn't allow more electrons between them. And so to get a double bond, you have to make a single bond, which would be sigma, and then you'd have to make a pi bond, which is going to be above and below that single bond. By the way, a triple bond is going to have those coming in and out, and I'll show you the pictures in a bit. One of the things I want to point out here is that pi actually makes this a little easy to remember. So sigma is directly overlapping. Notice the pi symbol is above, across, down, as if it is being shared above the floor, right? So if you think of the single bond as the floor as well, this is the pi bond, which is being shared above and below the floor, right? So it's sort of an easy way to remember, if you will. All right, so right here is where we start looking at and seeing examples of sp2 hybridized atoms and molecules. And so remember, when we talk about the atoms, that is where the hybrid orbitals are being formed and used, okay? The molecules will have atoms that have those hybridizations. The molecule here is not sp2 hybridized, okay? This carbon is sp2 hybridized. This carbon is another sp2 hybridized carbon. Okay? This right here, this hydrogen, doesn't have any hybridization. It just has an s orbital, period. So if we talk about this hydrogen here, it doesn't have any hybridization. Okay? So when we talk about hybridization, you need to keep in mind that we're looking at a specific atom. For example, this carbon or this carbon. Okay? So right here we have two sp2 hybridized carbons. They're forming a single bond or sigma bond right here. And that's direct overlap, sharing those electrons. This carbon then is forming another sigma bond right here to this hydrogen. By the way, hydrogen can only ever form a sigma bond because it only has the s orbital to work with. That's it. Can't even hybridize. It can't do anything else. Okay? All right. So then we are going to form a pi bond. This pi bond is going to be between these two carbons. They are going to use the p orbitals, not a hybridized orbital, only the p orbital between these two carbons. So it's going to use these two p orbitals, this one and this one, on these two different carbons. These are going to, this overlapping on the side p orbital is going to share electrons between them in what is called a pi bond. Okay? Notice this is a single pi bond being formed between these two p orbitals, one on each atom. All right. By the way, I know that it always shows you these electrons like perfectly in one side of it or something weird like that, and they're always being evenly shared, and it always looks so nice and neat, right? But electrons are not stationary, static things that orbit stuff. Okay? They pop in and out of existence, literally out of existence, do not transfer, do not go through the space in between, and they are messy. Okay? They tend to pop, they could spend time here, they can end up over here next, then over here, and you never know. Alright? So, but this is a nice way to look at these, and we never really keep track of the electrons themselves. We usually keep track of the orbitals. Now, saying that, this month, 2020, in the last 2 months, they made a huge breakthrough and were able to actually track individual electrons. And so there's actually been, over the last 3 months, you didn't hear about any of it because there's bigger news items. But some seriously major breakthroughs that could change the life as we know it. Like 2 major breakthroughs that might make global warming a non-issue in about 5 years. So, yeah, some big stuff. But let's go on with orbitals. So sp hybridization. This is going to involve one s and one p orbital. Again, how do you know that? Well, you just look at the name, right? Sp hybrid. So that means it is going to be an s, because there's no other number there, so just one, and a p, there's no other number there, so just one, mixing together. And that's it. So this is going to have 2 effective pairs around an atom. They'll always require sp hybridization of that atom. Think of straight line, okay? This is going to be your linear. So, for example, the carbon atoms in carbon dioxide are going to have an sp hybridization. And again, this is going to be 2 domains, right? So you only have 2 domains, which is why you only have 2 orbitals being made with your hybridization. So this is going to be used in the formation typically of pi bonds, either 2 double bonds or a triple bond. That is where you will typically see sp hybridized orbitals. And so right here again we have our hybridization going on. We have an s and a p. They're joining together. They make 2 hybrid orbitals, which are both sp hybrid orbitals. The whole concept being sp hybridization, right? And the distance of maximum separation is, well, just straight. It's a line, linear. Okay, so right here is an example of this. And so here we have a carbon. It has an sp, two sp hybrid orbitals. They will have direct overlap with this oxygen right here. So we have one overlapping this oxygen, one overlapping this oxygen. By the way, the oxygens actually have sp2 hybridization here. So again, remember, whenever we talk about the hybridization, you always got to specify the atom. You're always looking at a single atom that you got to look at. So here's our sp hybridization. Well, you might have already caught on that, wait, Dr. Clausen, that is not showing me all my orbitals. And you're right, it's not showing all the orbitals. We're missing two p orbitals here, aren't we? We only have 2 of the 4 orbitals we should have. And so what's going on? Well, 2 of those p orbitals aren't getting used for hybridization. So right here again we have our hybridization energy diagram. And we're mixing an s and a p orbital. And so that means we make 2 hybrid orbitals that are both sp. They'll be degenerate, they will be the same energy. We are leaving p orbitals, 2 of them. So we have 2 p orbitals we've left, we haven't done anything with. They're the same energy again. Again, that's called degenerate. And so again, yes, we do have our 4 orbitals. It's just that 2 of those orbitals are still p orbitals. And they're still going to have 90 degrees. One will be up and down, above and below, the single bonds. The other will be in and out, one lobe of this orbital coming out towards you, one lobe of this orbital going away from you. All right, so this is what this ends up looking like on an orbital level. So this would be CO2. CO2 has a double bond going to this oxygen, between this oxygen and carbon, has another double bond between this carbon and this oxygen. And that would be your CO2. Carbon dioxide, which is what you're breathing out this entire time. So right here we have our sigma bond. This is going to be the direct overlap between our hybridized orbitals here. Now, this is, remember, sp hybrid orbital. The other thing we have going on in this double bond here is we have a pi bond, which will be towards you and away from you. You see that these are the ones towards you and away from you. Okay, and this side we again have a sigma bond right here, direct overlap. And then we have above and below. And again, that is going to be our pi bond. So let's describe the bonding in the N2 molecule. All right, so let's describe this bonding in our N2 molecule. Sorry I repeated, I had to get a drink. So first off, you should try and attempt the Lewis structure. And if you don't understand Lewis structures, you really need to go back and review. There are practice problems. I've given you the slideshows from that chapter. I've given you instructional videos, multiple ones. Go back and practice, seriously. If you don't remember how to do Lewis structures, you can't accomplish them. You're going to find this chapter impossible. And sadly to say, most of you are going on to organic chemistry probably, or some sort of organic chemistry-like thing. And you will find that absolutely impossible to do without Lewis structure. You will find yourself failing horribly and spending a lot of money to fail. So please, please get down Lewis structures and these orbitals as best as possible if you're going on especially. But I would prefer if you just get it down for this class anyways. All right, so the Lewis structure for this has a triple bond. It has 2 lone pairs on either side of this. And so first off, let's try to count up our electron domains. So we have an area right here that would be an electron domain. And then we have another area right here, which would be another domain. These all have to move as one unit, don't they? You can't split up your triple bond. Your triple bond is called a triple bond. Notice the bond part only is singular. And so that means it's all one unit. Now notice when we talk about these electron domains, we always have to talk about a center. Much like when I talk about symmetry around a person or an object, I'm always talking about a central object, not like their finger has this symmetry versus their chest. Okay? you have to concentrate on one area to talk about any sort of shapes. All right, so we have our two electron domains. Well, automatically that means I can very quickly figure out this hybridization, can't I? And so if I talk about hybridization, I have two areas they need to be. That means I have two units they need to be in. And that means I have a hybridization that will have two orbitals in it. And that would be your S is in every hybridization because that's your lowest energy orbital. And then a single p orbital for an sp hybridization because again that would be 2, wouldn't it? And so each nitrogen right here is again two effective pairs, is what your book calls it. Seriously, domains is a better word, but in case you're looking at your book, there you go. And this is going to give you your linear arrangement, which means this is actually a straight line. You probably could have figured that out, that the molecule looks like a straight line, simply because there's two atoms, two things can only make a line. You can't make anything else out of only two things. This is going to be an sp hybridization again, like I said before, because they are in two different directions. That means you need two straight overlapping orbitals to make two different directions, don't you? All right. So each of these atoms, again, each of the nitrogen atoms is going to have two sp hybrid orbitals. They will also have two p orbitals, which we did not use. And those p orbitals, those are what are making our double and triple part of our bond, which again, this would be a sigma, then a pi, and another pi bond. All right, excellent. Remember that when we're talking about these pi bonds, those pi bonds are always composed of two p orbitals overlapping on the sides, okay? And so each of those pi bonds has two p orbitals that are parallel overlapping on their sides. And again, this actually explains our structure and electron arrangement that we saw from our Lewis structure. What is creating these Lewis structures that we've been seeing are actually the arrangement and filling of these orbitals with electrons, okay? It's not the Lewis structures creating these. We're using the Lewis structures to make figuring these out easier. But the relationship is that the orbitals are creating the chemistry, okay? And that's actually what the periodic table pattern is being created from. It's filling those orbitals up. All right, so this is an example of a triple bond like we see in this N2. Again, you have a direct overlap, which is our sigma bond, and then two indirect overlaps, which are going to be our pi bonds. By the way, these right here are localized electrons. That means that they can't go anywhere else. That's where that terminology comes from. So if I'm trying to find these electrons, I can just point and go, bam, they're somewhere here. They have to be, okay? They're somewhere in between. And I don't have to go, oh, they're somewhere in the molecule, I don't know where, okay? All right, so remember that this other sp orbital out here, this is actually where your lone pairs are located. So right here is one lone pair, right here is another lone pair on the other nitrogen. All right, now there is dsp3 hybridization. This is only going to happen when you have something from period 3 and below. So if you remember, the d block is where the transition metals are. So that is your d block orbitals. Now, those orbitals are actually created on the third period, but they don't get used until the fourth period normally. And that's because they're very high energy. However, as soon as you've been on the third period on your periodic table, any element on the third period has d orbitals that it could use. They're not that high energy that they just can't be used, okay? They are usable If you have enough electrons and it's high energy enough, they'll start getting filled and they'll make hybrid orbitals. And so, for example, here we have a phosphorus, and it is making a dsp3 hybridized orbitals, or hybridization. Now, that means that this is going to have a single d orbital. There are 5 of these d orbitals. There is a single d orbital that's being used in this that's mixing with an s, a single s, and then 3 p orbitals. Okay? 3 of the p orbitals. There are only 3 in that period. Now, this dsp3 hybridization, we just count up the number of letters in here. So 1, 2, and then another 3. This would give us 5 orbitals. And so we can see here that there's 1, 2, 3, 4, 5. 5 orbitals. This makes what is called a trigonal bipyramidal arrangement. And so it makes an arrangement that looks like this. Right here we have a triangle that's on one plane, see that? And then we have another orbital above and below. And so that is a trigonal triangle base, 2 pyramids. See the pyramid right here and then down here. All right. So right here is an example of something that uses a dsp3 hybridization, and that is PCl5. We have 5 chlorines around a phosphorus. And so this is surrounded by our 5 domains. See that? 1, 2, 3, 4, 5. 5 separate domains requiring 5 different orbitals. And so our phosphorus has a dsp3 hybridization. Our chlorines, on the other hand, do not. They have sp3 hybridization, the normal tetrahedral shape. And that is because they have 1, 2, 3, 4 domains. See that? They have different hybridizations. Remember, you're always talking about atoms when you talk about hybridizations. All right. So let's describe the bonding in a triiodide ion. Now remember, when you do this, don't forget to add the extra electron that this negative sign right here dictates. And so when we do the Lewis structure, a correct way to do the Lewis structures, again, just like I show you in those videos on how to do Lewis structures, or your book if you want to go back to your book. And if it's negative, you'd put brackets around it and a negative sign to dictate that that is negative. Remember that you would add up your electrons in your valence shell from the groups on your periodic table, and then you would add a single extra electron because that is a -1 charge. Electrons have a -1 charge. Okay, so we have our Lewis structure now. We see that this is 2 single bonds, and so that is 2 bonding electron domains here on this central iodide. And so the central iodide also then has 1, 2, 3 lone pairs. Those lone pairs would be 3 non-bonding electron domains. That gives us a total of 1, 2, 3, 4, 5 electron domains around this central atom here. And so 5 electron domains means you need a hybridization that will give you 5 orbitals. And so that would be an S, 3 P's, because there's only 3 P's, there's not any extras, and then a D. Now typically this would be called dsp3. That is actually the most normal terminology. However, you can find it in chemistry. It is not actually incorrect per se to call it sp3d. That is actually a possibility to call it. I don't know why they decided to put D first. It's sort of a weird thing, but it did happen. Now, the central iodide atom, again, that's 5 pairs. That will give us our trigonal bipyramidal arrangement. 5 groups. Maximum separation has to give us a triangle and then 2 pyramids above and below. All right. Now, Oh, the outer iodine atoms. Again, we count up our groups. So 1, 2, 3. That would be 3 groups right there. They're non-bonding lone pairs. And then 1 that's in a bond. And so that's a total of 4. And as we remember, 4 is sp3 hybridization. And that would mean a tetrahedral arrangement. And then this one's the exact same, so whatever, we're done with that. All right, now we got all that. And all of these bonds, by the way, because they're direct overlaps, there's no double, there's triple bonds, they're all single bonds, they all have to be sigma bonds. So we do not have any pi bonds here. That is not something we need to worry about. All right, so finally, we have gotten to the 6 electron domains. All right, so this is your 6 electron domains. Again, we have a single s orbital in any period, and then we have up to 3 p orbitals in any period, in periods 2 and below actually. And then in periods 3 and below, we have up to 5 d orbitals. You won't ever get to use all 5. I don't know of anything that uses anywhere near that many d orbitals in hybridization. But we will get up to the d2. What that means is it will use a single s orbital from that period. It will mix with the 3 p orbitals in that period. And then we will mix 2 d orbitals into that. And that gives us a total of 6 orbitals that are mixing. For a hybridization, that will give us 6 hybrid orbitals. Those 6 hybrid orbitals can point equal energy in 6 different directions, which means they will be the best energetic solution, the most stable version of something that has 6 different directions it needs to point in, 6 different groups or electron domains that are surrounding it. And so right here we see an example of that, which is SF6. All right. This takes up an octahedral shape, by the way. If you pay attention to this, if you sort of draw in the faces of facets between these different vertices, that's what the points on this would be called, you will see that this would be an octahedral, okay? And so this is an octahedral sulfur atom in the middle here with D2sp3 hybridized orbitals surrounding it. All right, so let's look at how the xenon atom in ZeF4 is hybridized. And so the first thing we have to do is we have to look at, well, what does Ze have for electrons around it? And so if you're having trouble figuring this out, I highly recommend you just go ahead and do Lewis structures. But you're going to find out that the Ze and ZeF4 has 6 pairs of electrons around the xenon, or 6 domains, that will be arranged octahedrally to minimize the repulsions. And so that means you have 6 groups. 6 groups would mean you'd have to have a D2sp3 hybridization around the xenon atom. Remember again, we always have to be talking about an atom, so this is xenon that we're talking about. And it will look like so. So you will see that it has these 4 right here, which are your fluorines that are on your D2sp3 hybrid orbitals right there. Then you have 2 more D2sp3 hybrid orbitals that are pointing up and down, and these will have your lone pairs. Now, an interesting little piece of information here is lone pairs always take up a bit more space than their atom equivalents. So any domain that has lone pairs always takes up more space and always has to be excluded away from any other lone pairs. That's why you always get things like this, where the lone pairs are on opposite sides. And that's because they don't have nuclei containing them, so they spread out more. All right, and there we go. Okay, so this is your general problem solving strategy, which I've already went with you like half a dozen times. Again, if you forget, here it is again. Right here, this is the number of effective pairs or the number of domains versus the shape that's being made and the hybridization. And so right here you can see those. Keep in mind that when we talk about these shapes right here, these are actually the shapes of the electrons. Okay? And so this is typically what's called the electron or electronic geometry. Okay? It is different than the molecular geometry, which would only be the atoms. You would exclude the lone pairs, the non-bonding. Okay. So let's do some practice problems. Again, please stop me, pause, and then try these on your own, and then go, well, what did he answer? What did he say? So for each of the following molecules or ions, predict the hybridization of each atom and describe the molecular structure. And so right here we have CO, BF4 minus, ZeF2. So the first thing we always have to do is we have to come up with that Lewis structure. And so CO molecule that has 10 valence electrons. And so once we do the Lewis structure, we're going to get this right here. And you'll notice it has a triple bond here, and then lone pair right there on each side. And so, again, now we're going to look at each of these atoms separately, because remember, whenever we do these hybridizations and everything, we always have to look at the atoms separately, okay? And so first off, let's describe the structure. That looks like a straight line to me, huh? And it is. It's a straight line. It's called linear. Now, the next thing we're going to do is the hybridization, because again, we don't actually have to go on any further. It's actually quite simple. So how many electron domains are there? Well, there's one and then two. And if there's two of them, that means there is an sp hybridization here. Again, that's two electron domains here. And so that has to be an sp hybridization again. Again, it really is that simple. You do not have to make this complicated. Because all orbitals are is places where you'll find electrons. That's it. Okay? All right, now your triple bond. What is a triple bond made of? Well, a triple bond is made out of a sigma and two pi bonds, right? And so that's what that triple bond is. It's a sigma and then two pi bonds. One above and below, one in and out. One coming towards you and one going away from you, right? And what are these made out of? Well, the direct overlap, those are made out of an sp hybrid orbital coming from the carbon, and overlapping with an sp hybrid orbital coming from the oxygen. Those direct overlap make your sigma bond. The pi bonds are made out of a p orbital here, overlapping to the side with a parallel p orbital here. Remember, they have two lobes, so up and down. And then you have the third bond, which would be another pi bond, being made by p orbitals coming in and out of the plane, overlapping on their sides when they are parallel. All right, how about these lone pairs here? Well, again, that's going to be your other sp hybrid orbital coming out the other direction, right? And so that will give you your lone pair here. This right here has an sp hybrid orbital coming out this direction away from it. Again, that gives you your lone pair. So in this case, the electron geometry and the molecular geometry are both linear. There actually isn't any difference. This is what they look like again. There's your sigma with your sps, lone pairs. There's your pi bonds right there. All right, so BF4 negative ion. This is going to have 32 valence electrons. The boron atom has to be surrounded by 4 pairs of electrons here. And so those would be your 4 groups. Now, if it has 4 groups around it, that means it has to be an sp3 hybridized orbitals or hybridization on the boron atom. That also would mean that it has to be in a tetrahedral arrangement, which is how you use maximum separation for 4 different things. And so right here we see the tetrahedral arrangement. That's the fluorines bonded, one up, and these other three pointing down in a sort of camera stand looking thing, or a tripod, if you will. Right here is actually the Lewis structure. This brackets, don't forget, is for the negative charge being on this whole molecule. And there we go. So in our boron, we have these four groups. They're all sigma bonds. This is an sp3 hybridization. There you go. This fluorines also have three lone pairs and finally a sigma bond. And so they also have sp3 hybridization on our fluorines right here. And that's again our three lone pairs right there and our sigma bond right there. And so again, that is four different things. That is an sp3 hybridization, which would make a tetrahedral arrangement around the fluorines. So in this case, the boron would have both an electronic and molecular structure. This BF4 would be a tetrahedral arrangement or geometry. So this would be a tetrahedral molecular structure, but also a tetrahedral electronic structure or electron geometry. All right, so ZeF2, this has 22 valence electrons. The xenon atom here will end up being surrounded by 5 electron pairs. Let me go ahead and get the Lewis structure up here. So right here is our Lewis structure, if we go ahead and do that. And you can see that we again have our xenon. It has 2 sigma bonds and then 3 lone pairs. That is going to be 5 electron domains here. Alright, so our 5 domains, that means we have to have 5 different orbitals pointing in different directions. And so our hybridization will have to have 5 orbitals going into it. That will be 1 s orbital. That will be then 3 p orbitals going into that. That would be 4. And then our 5th one would be a d orbital because there's no more others. So that 5th one is d. And so this would be our dsp3 hybridization, wouldn't it? And this is going to make our trigonal bipyramidal structure. Again, a triangle, which are these lone pairs, and a fluorine going up, a fluorine going down to make pyramids. All right. So the lone pairs end up having to be placed the maximum separation they can get. And what that means is these are 120 degree separations between them right here. These fluorines are actually only 90 degree separations from all these. And so these fluorines have to go up here above and below where they will be the closest to things, whereas the lone pairs need the furthest distance away from everything else. Alright, so our fluorine atoms, on the other hand, those also have 4 electron groups around them. So these fluorines has 1, 2, 3 lone pairs and a sigma bond. So that's 4 electron domains. 4 electron domains would mean an sp3 hybridization. It would also mean a tetrahedral arrangement. Remember, hybridizations are geometries. Geometries are hybridizations. There's not actually any separation there, okay? It's just whether we're talking about atoms that confuses the point. That confusion is entirely something you introduce to this, okay? All right. So this molecule right here, if we were looking at just the atoms, which would be our molecular geometry, you will see that the atoms are actually in a linear arrangement. So the electronic geometry or the electron geometry, that would be this trigonal bipyramidal. The molecular geometry, which is just the atoms, is linear. So let's join in with some questions real quick. And again, pause please before you go on to my answers. Which of the following molecules contains a nitrogen atom that is sp2 hybridized? And so that would be NO3 minus. Now, there's two different ways to do this. There's the long and the short way. The long way will always get you it right, and you never have to really worry about screwing it up as long as you understand what you're doing. The long way is just to write out the Lewis structure, and then again count up your electron domains, and then, well, the hybridization always has to equal your number of electron domains, right? So in this case, we would have 3 electron domains, and that would be sp2 hybridized. Okay, so what's the short way? Well, the short way is for you to understand groups. Groups are going to have similar arrangements, geometries, because they have the same numbers of valence electrons. And so what that means is if you've done one nitrogen, you actually know pretty much all nitrogens. So nitrogen has a lone pair. And that means you just go ahead and count up the things that's attached to, and that would give you plus your one lone pair that nitrogen always seems to have. And that's going to give you your hybridization number, or your number of groups, right? And so right here we'd go, and well, nitrogen has one lone pair, and there's 3 things attached to it. So that'd be 4. Well, this is 3, isn't it? 1, and then plus 2 for 3. This right here, well, this one doesn't actually have a lone pair anymore because it's getting over bonded. So this one right here is actually going to have 1. Okay, sorry for the sort of abrupt jump there. I decided that it's just too much of a pain in the butt for me to try to describe this with words, and I need a picture. So here's a picture of what this looks like. And so if you did the Lewis structure for this, this is what you'd get. So right here we can see that this right here is not going to have a lone pair because it's going to have more bonding to it than you would normally have. Because remember, these oxygens, they typically require 2 bonds. So they're going to gobble up that lone pair. Now, that would mean that this would only have 3 things going to it. Okay? And that means you would have an sp2 hybridization. Well, nitrogen right here, N2, that is going to make a triple bond between it. That's going to give you a lone pair and 1 nitrogen attached to the other, which is 2 things, which would give you an sp hybridization. Right here, you have a carbon attached to the nitrogen, and that's it. So nitrogen has its lone pair still, and it would have, well, to make up for all the bonds, it would be a triple bond. But that's only one other thing attached to it. So you have a lone pair, something attached to it, that's 2 different directions, and that would be sp hybridization again. If you want to do it the long way, it won't hurt you in the long run. You'll just get better and better at it, and eventually you'll get so fast it won't make a huge difference. But you can logically deduct these things. So what is the hybridization of Cl in the molecule ClF3? And so that, I probably should just, okay, so I probably should have went on, oh well. I guess I already showed you the answer here, it's DSP3. But we're going to go ahead and describe it even with the answer up there. Alright, so what I want you to remember here is Cl, chlorine, looking in the periodic table, and what you'll find when you look on that periodic table is it has 7 electrons already in that valence shell. And so what that means is this is almost certainly an extra octet, okay? Cl would normally only make 1 bond to get to its noble gas, right? And so that means automatically you should already be thinking, oh, it's probably going to be something up here, okay? Now, when you look at this, we have those 7 electrons, right? So each bond is going to have 1 electron input into these fluorines to give each of these fluorines 8 electrons. What that means is you have 3 electrons coming off of that 7 RAN to make those 3 bonds. Okay? And so that will be 3 bonds plus 2 lone pairs, which would be the remaining 4 electrons. And so that is 3 plus 2, which is 5. And so 5 would be D is 1, S is another, and then you have 3 P's. And so that would be 5. So 5 directions, 5 orbitals making bonds. That would give you your DSP3 hybridization. Again, don't think you have to do it this logical way. It is fine if you want to do the Lewis structure. Again, all you would do is just write out your Lewis structure, which is, at this point in time, I would hope you've practiced enough that it's like breathing. And then you would just take and figure out your number of electron groups around it, and that number of electron groups, count them up. That is the number of orbitals in your hybridization. That's it. And that would be 5 as well. Alright, so atoms that obey the octet rule and are sp3, hybridized, form blank pi bonds. So you remember when I talked about sp3 hybridization, I said that they are always sigma bonds. And so they cannot make pi bonds. The big thing you can remember is pi as in p, right? To make a pi bond, you actually need a free, not used in hybridization, p orbital. And if you have sp3, it's used all its p orbitals, not a chance, can't make it. You're already done. So what is the hybridization of the central atom in ICl4 minus? Go ahead and give it a pause bit. All right. So again, there's 2 ways of going about this. If you're confused about the ways that I'm saying it's a shortcut, and it's considerably faster, again, just do the Lewis structure, okay? It'll work perfectly every time. There really isn't any issue doing it. It doesn't even take that long. It'll be a guaranteed point for you, okay? However, if you want to do it the logical way, so again, Lewis structure, you would just write out the Lewis structure, count up your number of groups around it, and those number of groups would be, in this case, 6, and that would mean you would need 6 orbitals that are going in different directions, which would give you S, 3 P's, so that is 4, and then 5, 6. And so it would be a D2sp3. Now, the other way of doing this that is a logical way that you don't have to draw everything out, you can actually just look at a periodic table and deduct what it is you can look at iodine. You look at iodine on the periodic table. It's the unique thing. It has 7 electrons. Well, 4 of those electrons would have to make single bonds to this chlorines. And that means that you'd have 3 electrons left of the 7 that are not being bonded. You have to add an electron because there is an electron here that is making this negative. So that would give you 4 electrons not being bonded and 4 bonds. Well, lone pairs are going to electrons that are not bonded. So that would be 4 goes to 2 lone pairs or 2 non-bonding electron domains. And that means you would have 2 non-bonding domains, 4 bonding domains, which are these chlorines, and that would be a total of 6. And again, this would be 1, 4, 6. 6 electron domains. And so that would give you E, which is 6 electron domains, which is your D2sp3 hybridization. Which of the following has 2 pi bonds? Alright, so again, this is going to be something that you could very easily do with Lewis structures, which would be nice. That would be quite simple. The other way you can do this is, again, you can logically deduct this. So, I'm going to go ahead and grab the figure for the Lewis structure. Sorry for the... Alright, so that's actually what the Lewis structure is going to end up looking like. You're going to have a triple bond between the 2 carbons, and then a single bond on each side of these two carbons. And so if we count up our electron domains, again, we have one here and then one here. And so that's a total number of 2 electron domains. And that would give you 2 pi bonds, because remember that has to be a triple bond. Now, there's an easier way of doing this, in my opinion. Again, though, it requires more understanding. So it's like everything in life. If you want to do less work, you gotta be smarter about what you're doing, right? The dumber you get on what you're doing, the more work you're gonna end up doing. So the better your understanding here, the less work you need to do. So which of the following has 2 pi bonds? Okay, that tells me something that I need to make a triple bond between two things, right? And so all of these are carbons, aren't they? Okay, so that means in this case right here, I'd have one carbon, I have 4 bonds going to it. Well, carbon can only have 4 bonds. So those are all single bonds. In this case right here, well, my average would be, it's a 1 point something number of bonds, isn't it? It's definitely not a triple bond in there. Again, I'm just taking the ratio of these carbons to hydrogens here. You see that? And so right here, I see that, well, I only have one of each of these carbons having a bond being made to it from hydrogens. Hey, that has to be a triple bond then. That has to be 3 bonds I don't have accounted for, which is a triple bond, isn't it? And right here again, I would have, well, each of these has 2 hydrogens going to it. That means I can only have a double bond, can't I? And right here, well, each of these has 3 going to it. I'd have to have a single bond between these carbons. All right, honestly, the Lewis structure always works, but you can save yourself time and effort by doing this logically. So which of the following statements is true? A triple bond is composed of 2 sigma bonds and 1 pi bond. That is entirely opposite, isn't it? Sigma bonds result from head-to-head overlap of atomic orbitals. Hey, that makes some sort of sense. C, free rotation may occur about a double bond. Well, let's test that theory. Please take your fingers or 2 pencils, either one you want, overlap them, and then try to twist them so that they freely rotate around it without breaking anything. And you figure out you can't, can you? They always end up having to break one of the bonds to rotate. So that can't be right. Pi bonds have electron density on the internuclear axis. Every now and then I tend to give you guys something that doesn't really mean much. And I essentially give you something that sounds like it's somewhat complicated, because sometimes people like to just pick whatever they think sounds complicated. All this is saying is that it has the electron density between the 2 nuclei, right? And that's not true. That's not what a pi bond is. That's a sigma bond. And so it is B, which is sigma bond results from head-to-head overlap of atomic orbitals. The funny part is these 2 answers are actually pretty much directly opposite of each other. They're the same things, are opposite. All right, so which of the following has the shortest NO bond? So what I'm doing here is I'm comparing these different nitrogen-oxygen bonds and thinking about which one would be shortest. Now, there's 2 ways of looking at this. So when you look at single versus double versus triple bonds, the triple bond is the shortest, the double bond is the next shortest, or longer than the triple bond. The single bond is the longest bond. It's the one that will have the longest length. And again, that's because it's sort of your number of connections holding things together. So as you get more and more connections, you tend to shrink the bond. Okay? Now, this right here is also a question of positive versus negative. So right here we have a very high order bond, a lot of connections between them. We also have a positive. Positives have less electron density, meaning that they have to get closer to share that electron density between them. Negatives have greater electron density, so they do not have to get as close to share those electron density between them. So in this case, this is actually fairly clearly B. Um, Either way of thinking about it would have gotten me a B. So that's kind of nice, I guess. Which of the following statements about the CO3 2- ion is false? The orbitals on the carbon atom are sp2 hybridized. B. One CO bond is shorter than the other. And C. The ion has a total of 24 valence electrons. So in this case, if you remember anything about hybridization from your Lewis structures, you would pretty quickly realize that, well, B has to be wrong, just from the fact that hybridization exists, which is that when you write these out in Lewis structure, you're going to end up having to place single and double bonds between carbon and oxygens, and they'll look like they're different. But to make the complete picture of it, you would have to make 3 different versions where you'd have the double bonds placed between different carbon and oxygen. Now, what that means is that it isn't actually 3 different versions of this existing simultaneously. The reality is all of the carbon-oxygen bonds are the same. We just can't draw it properly. And so they're all the same. They're all partially between single and double bonds. And this one of them being shorter, is just wrong. The other way you could, of course, go about this is going through here and figuring out if these are correct. And so the orbitals on the carbon atom are sp2 hybridized. Well, there's 3 things going off this carbon atom. There's not going to be lone pairs on a carbon atom surrounded by oxygens, which are much more electronegative, a higher electronegativity. And that means that this only has 3 different directions. So the orbitals on the carbon atom are sp2 hybridized. Yes, yeah, they are. The ion has a total of 24 valence electrons. Well, you can just count up those valence electrons using periodic table. So we have carbon here, that's 4. We have 3 oxygens, that's 22. We have a 2 negative charge, that's another 2 electrons. That is a total of 24 valence electrons. Awesome. That means that B would have to be the wrong one, since we can verify the other 2. Of course, A could have been verified using a Lewis structure as well. All right, now, I know that I teach you these wonderful models and theories, and then I go and point out how they're wrong. And that it's true for this too. So the limitations of the localized electron model, which I've spent all this time teaching you, it incorrectly assumes that the electrons are localized. However, we do know that actually resonance exists. That means that not all electrons are localized. Some of them get shared. So not all of them are localized. Some of them are delocalized. It does not deal effectively with molecules containing unpaired electrons. What have I do with free radicals? I haven't even discussed it or made any sort of attempt to figure that out, have I? This does not provide direct information about the bond energies. All we do is sort of go, the hybridized orbitals are degenerate. We don't even think about it being different for being bonded to something versus not being bonded to something, or the differences between different bonds. So there's a lot of blank space here. And what's been done is there's sort of a correction. There's another theory that layers on top of this, and that is the molecular orbitals. So shorthand for that is MOs, as in molecular orbitals. By the way, you may be going, well then, wait, does that make atomic orbitals, the orbitals for just the atoms, AOs? Yes, it does. So AOs are the atomic orbitals, MOs would be orbitals for entire molecules. We don't even have to look at these specific atoms then. We just look at orbitals for the whole molecule. So the orbitals for molecules are going to have the same characteristics as atomic orbitals. Again, these orbitals, again, are going to hold 2 electrons with opposite spins. They have to be opposite spins It can hold up to 2 electrons for a molecular orbital. The square of the molecular orbital wave function is again going to be the electron probability. So what we're really looking at is not containers. We're looking at the probability of finding these electrons in a certain space. And again, that will be exactly like they were for atomic orbitals and molecular orbitals. So right here, this would be the simplest form of molecular orbitals. We're looking at a hydrogen bonding to another hydrogen. And so this would be H2, the molecule. And this is going to be the easiest way to look at it first. So we have, for every combination of orbitals, we can neither create nor destroy again. Again, this is the same sort of thing, right? We're really not changing the game. We're just adding another layer. It's just a little bit more detail. It's just MOs versus AOs, okay? So each hydrogen is going to have an atomic orbital. These atomic orbitals are going to mix together to make our molecular orbitals. So in the case of two hydrogens, each hydrogen has a 1s orbital, and that's all it has. So we have hydrogen A that has a 1s orbital, and that's what this means right here. We have then hydrogen B, the other hydrogen, that has a 1s orbital, and that's what this one is. These mix together. When they mix together to make our molecular orbitals, they're going to mix together to make two molecular orbitals because we had two atomic orbitals. That means that when we have two atomic orbitals, they have to make the exact same number of molecular orbitals. Okay? So, two atomic orbitals makes two molecular orbitals, and these are the two molecular orbitals. We have molecular orbital 1, which is the lowest energy one, molecular orbital 2, which is the higher energy one. Okay, so when S's overlap, they're going to make our molecular orbitals. Molecular orbital 1, this is going to be considered the bonding orbital. You will notice that the nuclei would be out here on the different sides. Our electrons will be shared in between. This is considered constructive, okay? And that means that this is the lowest energy one. It's the one that actually makes bonding happen. When you share the electrons between the nuclei, they're going to stick together, and we call that a bond. Okay, the other orbital that we're going to make is called destructive. It is an anti-bonding orbital. What that means is your nuclei are going to be here and here. And what that means is they will repel each other. This is actually the electrons causing the nuclei to be pulled apart. And so it is the exact opposite of bonding. If you have more electrons or an equal number of electrons in anti-bonding orbitals, your bond will be pulled apart. You won't bond. To bond, you have to have more electrons being shared, pulling the two atoms together, than they are pulling them apart. Okay? All right, so let's look at some of the properties of these molecular orbitals for these hydrogens. So the electron probability of both molecular orbitals is going to be centered along the line passing through the two nuclei. So molecular orbital 1 and molecular orbital 2 that I've already showed you were the sigma molecular orbitals. They are the sigma bonds, aren't they? And so we have our sigma bonding and our sigma anti-bonding, which is right here. So in our molecule, we would have the atoms right here. This is the same energy diagrams we've been seeing before. Just now we're going to mix them into molecular orbitals. So right here, this would be the energy diagram for a single hydrogen. And we see that it has a 1s orbital, it has an s orbital, that only has one electron in it. This is the other hydrogen. And again, it has the same energy, it's the same as the other one. I mean, there's hydrogen. This one's the B. It really doesn't matter whether it's A or B, no, but there you go. And it has a single electron in it, like you'd expect. And that single electron is located in an s orbital. There you go. All right, so when we mix these together, we will make molecular orbitals. One of them will be lower energy, which is because it's sharing electrons between two nuclei. So these are being stabilized more. And that's this orbital right here, which is our sigma orbital, or our molecular orbital 1, which is our sigma bonding orbital. All right, so the other orbital that this makes, remember we always have to have the same number of orbitals going in and out. We came in with 2, so we have to make 2. And so the other orbital we're making is going to be our antibonding orbital. This is going to be higher energy than the individual orbitals because you're literally pushing those electrons off onto the opposite direction away from the 2 nuclei being shared to only 1. And so it is higher energy. It's higher energy than an atom by itself. All right, so right here we have our antibonding sigma orbital, or our second molecular orbital we made, which is our antibonding one, which is high energy. Okay, so the next thing we're going to do is we have our orbitals being made. We always have to then fill in our electrons afterwards. And so we have 2 electrons going in. That means we have to have 2 electrons going out. And so we fill in those electrons on the lowest energy orbital first. Always, you fill the electrons in the lowest energy orbital first. So each orbital can always hold up to 2 electrons. We have a total of 2, so we have 1 electron we call up, we have 1 we call down. And those are the spins of the electrons, if you remember spin. We don't have any more electrons, so this doesn't have anything. Our antibonding is empty because we only had 2. If we only had 1 electron, we'd only have 1 here. Again, you cannot create or destroy electrons, you cannot create or destroy energy, you cannot create or destroy orbitals. Really, you just can't create or destroy anything. We always just recycle. All right, so let's look at bonding and anti-bonding orbitals a little bit more. Bonding molecular orbital is going to be lower energy than the atomic orbitals of which it is composed. The electrons in this orbital will favor the bonding, and that's why we call it bonding molecular orbital. They're ones that will be shared in some way and pull the 2 nuclei together, thus favoring bonding. Antibonding molecular orbitals. These will be higher energy than the atomic orbitals of which it is composed. The electrons in this orbital will favor the separated atoms. They will pull them apart. They will not contribute to pulling them together. All right, so again, this is that same sort of figure. This is what every single molecular orbital diagram will always look like. Okay? It is always going to be 2 different atoms, and they will make their molecular orbitals. For every single orbital you put in, you have to make an orbital coming out. So 2 orbitals in will make a bonding and antibonding. If you had 2 orbitals for each of these, they would make 2 bonding, 2 antibonding orbitals. It's just as simple as that. It's not something that needs to be complicated. The properties of these molecular orbitals. So the molecular orbital model is a physically reasonable model. There's a high probability of finding electrons between the nuclei and bonding molecular orbitals because, again, the nuclei are positive, the electrons are negative. They typically, again, end up being shared because they're both being pulled by both nuclei. Electrons are going to be outside of the space between the nuclei and anti-bonding molecular orbitals because those will be not sharing. Those will be the ones that do not share. Labels on molecular orbitals indicate their shape, the parent atomic orbitals, and whether they are bonding or anti-bonding. So anti-bonding character is always going to be indicated by an asterisk. And an asterisk, again, is that little star-looking symbol that you can see on your keyboard. And one of the things I would like to denote here and point out for anybody going on is if you pay attention, asterisks in general and sciences are going to be high energy conditions. So whenever you see an asterisk, that's usually a modified high energy condition. It is something that is typically higher energy than a ground state, a lower energy state. Okay. Molecular Electronic configurations can be written in the same way as atomic configurations. They're extremely similar. There really isn't much of a difference. They're just MOs instead of AOs, okay? Each molecular orbital can hold 2 electrons, and the spins always need to be opposite, because otherwise they would have the exact same energies, and that would mean that they've merged and blow up and the universe is gone. Now, I'm joking with you to some degree, but actually, if you try to make them obtain the same energy, you do get very energetic responses. Not universe gone or anything, but it's not really possible to do. But there is some science on that. That's kind of interesting. So molecular orbitals will always be conserved. The number of molecular orbitals will be the same as the number of atomic orbitals used to construct them. That is something you really should, as a modern human, just have as a baseline in everything you do and in everything you think, is that nothing's ever free. Okay? You always get the same in as the same out. You never can create nor destroy anything. Um, Everything is always using what you have to get what you get. Okay? Now, molecular orbital energy level diagrams for H2. We've seen this before. This one, however, has the terminology you're going to see from now on. And that is that you typically are going to write these hydrogen and then the orbital. So this came from a hydrogen. It is a 1s orbital right there. Then you have your electrons. You typically write in the electron starting with an up. If you don't have it down, you don't bother writing it down. That's it. All right, so now we have merged these. Notice we don't have any more labeling. We don't need any more. We merge these into our molecular orbitals. We're going to call this a sigma 1s. Notice there is no asterisk on this one because this is a bonding sigma orbital. It is composed from 1s orbitals, so it has 1s. This right here is the antibonding orbital, and it is a sigma asterisk star 1s. Again, it was made from 1s orbitals from these hydrogens, but it is the sigma straight on overlap, but is the antibonding, which means they're not in between, they're on the opposite sides. All right, so how do you determine what sort of bond we have? Now, you probably could have logically figured this out. So in a classroom, I would have stopped here and I would have talked to you guys a bit and gotten you guys to try to, with very little input from me, respond and build up to the next topic. Unfortunately, I can't really get your guys' responses very well. Even when I use things like Zoom and stuff, it doesn't work out very well. It just makes a mess. So what I'm going to do here is I'm sort of going to lead you on, if you will, and you can try to pause between so you can think of it yourself. Now, honestly, give this an attempt, okay? Because this is how you build your thinking and critical thinking skills. This is how you get so that you can be like Sherlock Holmes and deduct everything, okay? If you don't build these skills, you're gonna be like somebody, like a parrot. You won't be able to reason for yourself, okay? And that's a big problem because that means nobody has the ability to actually be fully functioning humans. So, however, let's try to make you the best human you can be. So, what I want you to do here is look at this diagram. Think about this diagram for a second. This diagram is of H2, a molecule that you have written out, used, talked about, and seen hundreds of times in the course of your chemistry career. This molecule has a single bond. Now, we've looked at a sigma bond before, haven't we? And this orbital right here is called a sigma bonding orbital. So this really has given you so many hints that you should by now be going, oh, when this is full, I've made a single bond. Okay, When I've put electrons into here, I'm causing this single bond to be split up, to not be made anymore. And this will be called bonding order, okay? That is going to be a number we can get from these diagrams that will tell us the number of bonds between two things, the bonding order, if you will. And so right here we have, right there is how you get it, is the number of bonding electrons. So the number of electrons in bonding orbitals. And that will be minus the number of anti-bonding electrons. The number of electrons, if any, that would be in anti-bonding orbitals. All right, now the number of electrons, each bond has 2 electrons in it, right? And so this number of electrons is going to have to be divided by 2 to give our bond order. And so we can see here we have 2 electrons in bonding orbitals, no electrons in anti-bonding orbitals. That would be 2 divided by 2. That would give us a bonding order of 1, which tells us this has a single bond and hydrogens bond together, which I hope you would realize, considering the elemental form of hydrogen is H2, and you've seen it hundreds of times. I would hope that's not a surprise. So these bonds are going to be perceived in terms of pairs of electrons being shared, cementing these two atoms together, or tearing them apart. Okay? The larger the bonding order, that means you have greater bond strength, and that means you have things like 2 would be a double bond, 3 would be a triple bond, and so on. Now, recognize that you can have a bonding order of 0.5, okay, or 1.5. That's entirely possible. You could also have a bonding order of 0. Now, if you had a bonding order of 0, what would that tell you? Well, if you have 0 bonds, that means you are not bonded, are you? So, if you have a bonding order of 0, yes, that does mean that there is no bond. It does not bond together. That's actually what we'll see when we do helium. If you have a bonding order of something like 1.5, that's what you see in cases like benzene, okay? That has a 1.5 bonds that are being represented by their resonance structures, where we alternate those double bonds. And so if you look up benzene and you remember benzene, that is an example of 1.5 bonds, or most of the resonance structures are going to end up being things like 1.5 bonds, 0.5 bonds, that sort of stuff, okay? That's actually where you start seeing those. All right, so let's look at this right here. Here we have an H2 negative, negatively charged ion. Again, when we have this, we have an extra electron. So we had this extra electron right here. This extra electron is going to end up going into the anti-bonding orbital, because that's the only place that has free space. Remember, every orbital can only have up to 2 electrons. So again, we do 2 electrons in bonding orbitals, minus 1 in an anti-bonding orbital, and divided by 2, because that's bonds versus electrons, right? There are 2 electrons in every bond. And so we find out that a H2 negative ion has a half bond. It is a half bond order. This is actually a very weak bond. This makes H2 negative very, very reactive. It would not be something you should breathe, whereas H2 is actually reasonably safe to breathe. It's not something I breathe a lot of, but you know, you'd be okay. H2 is flammable. H2 minus will just react to you and boom. You don't need to light it up. All right, so homonuclear diatomic molecules. Homo means same. Nuclear means as in nucleus, right? And so these are going to be same nucleus. So diatomic, di-2, atomic, atoms. So same nucleus on both sides, atoms, or molecules. So this is going to be composed of 2 identical atoms. Only the valence orbitals of the atoms are going to contribute to these, significantly to these molecular orbitals of any given molecule. What that means is you can safely just ignore the non-valence electrons. So for something like carbon, you can ignore that first S safely. You don't even have to worry about it. Just don't worry. So for example, right here is boron. The electron configuration of boron is 1s2. It has 2 electrons in its core, which is that 1s orbital right there. This right here is the valence electrons. Those are the ones in the outer part, the outer shell. And so this is 2s2. There's 2 electrons in its s orbital. Then you have 2p1. There's 1 electron in the p block in its p orbital. So B2 molecule, this is going to be described based on how p atomic orbitals combine to form their molecular orbitals. So the p orbitals, these are going to occur in sets of 3, which will be mutually perpendicular orbitals, meaning they're all perpendicular to each other and they make this cross sort of shape, right? 2 pairs of your p orbitals can overlap in a parallel fashion, meaning like this. See these 2 right here, which are your pi bonds, right? And 1 can actually overlap in an overlapping type, which is sigma bond. So let's consider these molecular orbitals from the head-on overlap first, since that's the sort of more simple thing we've already seen. So the bonding orbital is going to be formed by reversing the sign of your right orbital. So products, this is going to produce a constructive interference, and there is going to be an enhanced electron probability between your nuclei. What this is really saying to you is that the ones that overlap directly, which would be your sigma bonding orbitals, this is going to have a greater probability of finding electrons because you have your 2 nuclei that are interacting with them. Your anti-bonding orbital is going to be formed by direct combination of the orbitals, and this is actually going to produce your destructive interference. There will actually be a decreased probability between the nuclei, which means that this is the destructive anti-bonding, where the electrons are on the opposite sides, not between the 2 nuclei, not contributing to bonding. Molecular orbitals are going to be sigma molecular orbitals. In this case, for this bond, the combination of parallel p orbitals will match positive and negative phases. This will result in your constructive interference. When your p orbitals make bonding orbitals or constructive interference, they're going to give you your bonding pi orbitals. Okay, remember that side overlap that you talked about with your p orbitals overlapping to the side, not directly overlapping, is your pi orbitals. So again, this will be your bonding pi orbital that is going to share the electrons above and below, but between the 2 nuclei. If the signs of one orbital are reversed, this is actually going to give you your anti-bonding pi orbital. And these are again being non-directly, and you'll see this in just a bit, I'll show you pictures, but they're going to be not shared directly, and it's easier to see the deal. Just know that the p orbitals, they have pi molecular orbitals, and these pi molecular orbitals, the electron probability is going to be above and below the line between the nuclei, just like we talked about before. Again, like we talked about before, these pi orbitals, they're going to be made from p orbitals. So in this case, they'll be pi 2p orbitals. And you will make, for every combination of 2 atoms, giving you 2p orbitals, you will make a bonding pi molecular orbital and an anti-bonding pi molecular orbital. The bonding not having anything up here, the anti-bonding one having an asterisk. All right, so this is what your energy level diagram looks like. And so here we have boron and another boron. And these are going to combine their 3 molecular orbitals here into this combination. Notice these are all the pi atomic orbitals right here. So you have 3 p atomic orbitals right here, combining with another 3 from this atom, which gives you a total of 6 molecular orbitals. First, you have your lowest energy one here, which is going to be a sigma bonding orbital, made from your p atomic orbital from each of these. This right here is going to be two degenerate pi bonding orbitals. Again, these are made from p orbitals in these two borons. Okay, so those mixtures also are going to give you antibonding orbitals. So this right here is going to be a pi antibonding orbital made from 2p orbitals. This right here is going to give you a sigma antibonding orbital made from your p orbitals from each of these, from the second energy level. So we go in, we see that our boron has 2 electrons in the 2s orbital. That is the second energy level, second period, s orbital. These will just directly mix into this right here, which is the sigma and sigma star, which is the sigma bonding and anti-bonding orbitals. I would like to point out right now that you do not actually have to do this work down here. Anything that would, both of these atoms have p orbitals that you're using, will automatically have this filled up, okay? And because this will automatically be filled up, all of the math and everything you do for it will be pointless. So, if you do anything from the p block, which is boron on over to the right, you are going to end up just caring about this. If you do this part, it's always going to end up being the exact same thing, and you won't care at all, okay? But you can. It's fine if you do it. It won't cause you problems. It just is extra work. All right. So here's the important part. These are the p orbitals. One of your p orbitals will have a direct overlap. By the way, because this has bonding and anti-bonding orbitals here, this is not actually bonding here. This is just busy work to account for the electrons, okay? When it comes down to it. This right here is your sigma direct overlap from your p orbitals. Each of these has one electron, because boron is the first one in the p block, so it has one electron each. So we will fill in the lowest energy, which is our sigma bonding orbital, and this will be an up and a down, which is our 2 electrons, and so that's it. We're done. We don't have any more electrons put in here. That's over. Okay. So, one of the other things I would like to point out, typically the sigma is always going to be the lowest and highest energy. They are normally the lowest and highest energy orbitals. And the reason for that is because sigma is either direct overlap or directly pulling them apart. There isn't any real middle ground there, right? They're either the lowest energy, which is the most stable, or the least stable, which is directly just pulling the dang atoms apart. Pi, on the other hand, is more subtle. Pi is above and below. So you don't have both atoms getting to pull on the electrons equally, even when they're between. They're above and below, right? So you don't have the most direct pull on them, the most direct sharing. And so it typically is a little bit higher energy for the bonding. However, the anti-bonding will not be directly pulling the two atoms apart either. And so you do get a little bit of attraction usually. And that means that these anti-bonding pi orbitals typically are not as high energy either. Now, let's look at the bond order first here and just do it like this with everything written out so that we can keep things straight. So, we look at this bonding order. We count up our number of electrons that are in bonding orbitals. This right here is a bonding orbital, and so is this. So that is 2, 4. That is 4 electrons. Then it'll be minus the ones that are in anti-bonding. This right here is an anti-bonding orbital that is 2 electrons. So we have 2 electrons remaining. That will then be divided by 2, which would give us a bond order of 1, which means boron has B2 has a stable molecule that has a bond between it, which is bond order 1. Alright, so let me point out the slightly easier way of doing this. If both of your atoms come from the p block, again, that is the boron, carbon, nitrogen, oxygen, fluorine, all of those things, then you can actually save yourself some time. What you can do is just not write this in. Okay? Recognize that your s block, it's always going to be full. Both of them will always have 2 electrons in s because you're beyond s. You're in the p block, right? And so you just don't write any of this out. You don't count the s electrons. You don't count the electrons that would be in the s orbitals. You just ignore them. And what you do is you just count how many spaces over it is in the p block. Okay, that block on the right that has 6 spots going across starts with boron. And so that p block, in the case of boron, has 1 electron. In the p block, you have 3 orbitals possible, which are the p orbitals, right? Px, py, pz. By the way, if you ever forget, all you have to do is count across from boron over to the noble gas, and that would be twice the number of orbitals. There you go, because the periodic table is based on the orbitals. Now, again, you would just put in 1 electron for each because there's only 1 electron in that p block. Again, you would put these same orbitals, same way, just like this. You're just not doing this part. And you would get the same answer here. Okay, so let's try the bond order. What would happen then? So, did you notice that we added 2 and then subtracted 2 because of this stuff? Because this isn't really bonding, it's just counting. That's all we're doing. So we added 2 and then subtracted 2 off. We will always end up, for every single atom, for every single element that's in the p block, adding 2 and subtracting 2 from the s block every time. We'll do that every single time whenever we do bonding order. And so it ends up not making any difference. So let's try this. Let's just do this block. So if we don't even do this, we just ignore it. We have 2 electrons in our sigma bonding orbital. And that's it. Then we look here in our anti-bonding orbitals, we don't have any electrons. And so we would take 2 minus 0, that's 2, divided by 2. Well, that would be 1, just like we got here. So you see that ends up not making any difference. You can actually just do it without doing the s orbitals at all. If you did not understand what I just said, where you do not need to do the s orbitals, etc., etc., if you do not understand that for whatever reason, feel free to write it in every time. There is no reason not to write this in. It won't cause you problems. It just saves you time if you can skip it. All right, so magnetism. Many of you may have sort of wondered what's going on when you take a CAT scan, or you may have heard of an MRI. These are all built off of this conception that we're talking about right here, okay? Which is para and diamagnetism, which is all based on these orbital stuff we've been doing. So paramagnetism is going to be a substance is attracted into the inducing magnetic field. So if you put a paramagnetic substance between 2 poles of a magnetic field, usually has to be fairly strong, it will actually pull that substance into a tight band between these 2 magnets and cause it to line up in there. Diamagnetism. Diamagnetism, the substance is repelled from the inducing magnetic field. So again, if you do a magnetic field with a diamagnetic substance around it, it will actually push the diamagnetic substance out and cause it not to line up in between those 2 magnets. So this is going to be associated with paired electrons. One of the ways you can sort of remember this is if you have unpaired electrons, you can get them to line up easier because the electron doesn't have sign canceling it. If you have an if you have all paired electrons, then every time you try to line one electron up, the other one is going to end up going opposite of it. Okay? So, a substance that has both paired and unpaired electrons will actually exhibit net paramagnetism. So, net paramagnetism right here. Uh, Again, you're looking at atoms in this case, molecular orbitals, count-ups. Um, this would be a bulk substance, something like you may have realized that like iron has steel, or steel oftentimes has spots where it's just pure iron, or you could have a substance that has two different molecules in it. Okay. Again, if it has unpaired electrons in it, though, it will overall give you a paramagnetism overall net. Okay, so this is actually how you would measure this. You would take your sample, you would put it in a glass tube, you'd apply a magnetic field, and this sample tube right here would be suspended in this outer glass tube, which is typically a vacuum, and it would be suspended by a very delicate balance that would cancel out gravity. Okay? And so what then you're looking for is when you turn this electromagnetic field on, if it's exhibiting paramagnetism, it's going to get pulled into that inducing magnetic field, into the magnetic field. Okay? And so this tube will get pulled down into this magnetic field. If it is diamagnetic, it's actually going to get pushed up. Okay? And so that would then measure how paramagnetic it is and whether it is paramagnetic or not. Okay, so now let's look at this diagram here. So we have B2 we've already done, and this gives us a little bit of something to work with. All right, so here we have the energy diagram for B2. This is the actual energy diagram. What you will notice is it looks a bit different than what we did before. Again, we can pretty much ignore the s orbital stuff. Just ignore it. Don't worry about it. It doesn't need to be looked at in this case. Okay? What we really need to look at is what are the p orbitals doing? And the other thing that is important is whether the p orbitals actually mix with the s orbitals. Now, you don't see the ps mixing in this notation. What ps mixing actually says and means is that when the p and s orbitals in the atoms are close enough in energy, your p and s orbitals can actually mix. And what this does is it causes the p orbitals to rearrange what is the high and low energies. Okay? So for example, when we allow the p and s orbitals to mix, and they do ps mixing is what this is called, the sigma and pi orbital actually flip. And so what we get is the pi orbitals, pi bonding orbitals. Remember, this is only going to be for the bonding orbitals, okay? The pi bonding orbitals will actually be on the bottom. The sigma bonding orbital will actually be the next highest energy. Again, this is only for the bonding orbitals. We do not have to worry about this for the anti-bonding orbitals. That's not the important part here, or the issue. Okay, so in this case, again, we distribute these two electrons. In this case, if you remember your rules for distributing electrons among the orbitals, you remember that you put one electron in each orbital that is degenerate first. So in this case, we distribute one up and then another up in a different orbital. And again, that's much like desks, right? When people typically line up and use the desks, if there's enough room, they'll go ahead and distribute one person per desk because you got more space, you can put your backpack and everything else. This means you've lowered the repulsion between these electrons, right? And so you give one in each. You will notice that this would be an unpaired electrons. This would be two unpaired electrons. And that means this would actually have paramagnetism observed in B2. Okay, so what if the p pi 2p orbitals were lower in energy than the sigma 2p orbitals, what would you expect the B2 molecular orbital energy level diagram to look like if you don't have any PS mixing? Okay, so first off, that's sort of the same thing. You don't have any PS mixing, you would expect this to be lower in energy. You would expect these two electrons to actually be in the same orbital. That would mean you'd have paired electrons. And that would mean that this would not be paramagnetic, but it would rather be diamagnetic. All right. And this right here sort of shows you where we don't consider PS mixing. All right, so yeah. So anyways, there we go. We got that. Make sure you practice a bit on it. Make sure you practice writing these out. I'll give you a few more examples. Remember, paramagnetic, they are unpaired, okay? One of the reasons you can remember this fairly easy, para, unpaired. Whereas diamagnetic, di is in duo, two. So diamagnetic, they're always going to be paired up, okay? And remember, diamagnetic, di is in two, is in they're paired, but also di is in diamagnetic field, and paramagnetic is in parachute in, I guess. I don't know what you want to go with that. But anyways, we'll try that. Right here, we see some different energy level diagrams. You may want to go ahead and practice generating these since we have a whole table of examples. And what you have here is, again, this is distributing these electrons, one in each, so we end up with paramagnetic for boron. If we want to figure out bond order, again, this is, we can just ignore all these. Yeah, they're all full all the time. So we can just ignore the S's and just look at this top part. And so here we go, 1, 2, bonding, and that's divided by 2, so it's bonding order of 1. Then we look here. This right here is going to be 2, 4, bonding, and that would be divided by 2, so bonding order 2. That's a double bond. That means it's going to have a bit more than twice the energy to break it, and it's going to be the shorter bond compared to boron. All right, so if you look here, you will notice that the sp mixing happens on the front half of the p block. So if you remember your periodic table, or if you go ahead and get it out, I'll wait. Okay, I'm glad I waited. I'm sorry, I have to joke a little bit. It's just really boring doing this by myself in a room. Anyways, it's much funner doing it in class. So, you have your PS mixing, your SP mixing occurring in the first half of your P block. What I mean by that, if you go on the periodic table, you will see that there's sort of a little block on the right hand of the periodic table that has the noble gases in it, but it also has, it starts with, on the left, top left of it, boron, carbon, and then nitrogen, and then goes on to oxygen, fluorine, and then the noble gas, which we don't need to put because the noble gas doesn't bond. Because the noble gas. But the bonding order for the noble gas would be 0. I'll actually show you an example of that in a bit here, but it's anticlimactic. So the PS mixing actually occurs on the first half of your SP mixing occurs on the first half of the P block. That is the B2, C2, and N2. On the second half of the P block, where you have doubling up on your orbitals, you actually do not have your SP mixing occurring anymore, which means on the second half from O2, F2, you will actually have the sigma being the lowest energy one. You will go back to normal, if you will. Remember, this is the abnormal state. This is the weird ones. Okay? I know it's 3 of the 5 examples here, but it is the weird ones. All right, so again with this, you would fill in 4 electrons for carbon on here, That would give you paired electrons. See, they're paired everywhere. There's no unpaired ones. And that means carbon C2 is actually diamagnetic. Into again, you would have another 2 electrons, which we fill in this one orbital right here. And that means this one is also diamagnetic. By the way, once you figure out one is diamagnetic and non-diamagnetic, it's actually kind of easy to do, because once you have this, every single time you increase one step on the periodic table, that actually gives you 2 extra electrons. See that? So this goes from 2 up here to 4 to 6 to 8 to 10. All right, so this is going to have sigma on the bottom, and so we fill that in. That has pi up here, and then we fill this one in, which is the top, is the anti-bonding pi orbitals, one into each, and that would give us paramagnetic, 2 unpaired electrons. Now notice when we do the bonding order, we again would count this up, and so that would be 2, 4, 6 bonding electrons minus 2 anti-bonding electrons, and so that would give us 4 divided by 2, which would be 2. Notice again, you could include these and you get the same answer. It don't matter. All right, so here we look at this. And again, we count up our number of bonding versus anti-bonding. And that's 2, 4, 6 bonding minus 2, 4 anti-bonding, leaving us 2 electrons, divide by 2, and we find out it is a bonding order of 1. You will again notice that the double bonds are somewhat close in how far they are, the distance. The single bonds are somewhat close in how far they are in the distance, and the triple bond is the shortest bond. Okay. One of the reasons you see differences, though, you will notice the energy is actually fairly different, and that is because fluorine is extremely electronegative. You're actually starting to see electronegativity effects. Okay, so here's some of the key points regarding the period 2 diatomics. One of the reasons we're talking so much about period 2 is period 1 is very simple bonding. It is actually, period 1 accounts for over 90% of the mass in the solar system. Period 2 is the almost is 90% of the remaining mass we're talking about in the solar system. And so we're up to 99.99 something percent once we go through period 2, okay? And they actually have more complicated bonding, which is more important. Now remember, there is a definite correlation between bond order, bond energy, and bond length. They are directly correlated. You can figure one from the other with a few other little key factors to make the exact numbers. Bond order cannot be associated with a particular bond energy. That is because you just simply need to factor in electronegativity. It's just that simple. You also have to factor in sizes. That actually makes a difference. N2 molecule will have a triple bond because of the large bond energy associated with it. The O2 molecule is paramagnetic. That's actually extremely important. That's a lot of the medical procedures and science has been built up off of that. Here is photoelectron spectroscopy, PES, for molecules. By the way, PES for molecules. An interesting side note is this is one of those things that's like pin number. Everybody says pin number, right? Or CAT scan. People always say PES spectroscopy, and the last word in the abbreviation is spectroscopy, so it's idiotic. By the way, PIN number is personal identification number, as you're saying it again. And when you say a PET scan, or a PET scan is the last word for that. PET scans are positron emission tomography. Tomography is actually a type of scan. So you're saying scan, which is kind of idiotic, but whatever. It's something people do, right? So this is going to provide us valuable information about the energy levels of the electrons in molecules, which in turn tells us what these molecular orbitals look like. This is an extremely useful tool for characterizing and testing our theories of bonding in molecules, figuring out if we have double bonds, triple bonds, what sort of bond strengths we have and energies. That's actually quite useful tool. Alright, so use the molecular orbital model to predict the bond order and magnetism of each of the following molecules. So we have Ne2 and P2. Now, first off, let me just say something here. Ne2 is full, right? Ne has full atomic orbitals, it has full molecular orbitals if they could bond. They don't bond, you should know that because it's a noble gas, right? So automatically, you don't have to actually do anything for Ne2. You could have just went, well, it's bonding order 0, it doesn't bond. And the magnetism, well, everything's paired up because it's full. It has to be paired up because it's full. But anyways, we'll do it. That's a good example. It's good practice. All right, so again, we're doing Ne2 right now. Sorry, no time for you guys, but I had to go grab some more water here. All right, so the valence orbitals for Ne are going to be the 2s and 2p orbitals that you would see on that second period. And remember, there will be 3 of those 2p orbitals. So the Ne molecule has 16 valence electrons. That's 8 valence electrons from each atom. And remember, that is actually the full octet. So that's your 8 valence electrons. So if we place these electrons into the appropriate molecular orbitals that we produce from our diagram, we would get something like this. Okay. So again, we have our sigma that comes from our s orbitals. We have the sigma, anti-bonding sigma. And then we have the sigma bonding from the 2p orbital right there. And then we have the pi one. Remember that we do not have sp mixing on the second half of the p block, which is where the Ne is located. It's on the second half, the right side of it. Okay, so we get our pi bonding. There's 2 of those, and then we have our pi anti-bonding, 2 of those, and then finally our sigma anti-bonding, which again, there's only 1 of those orbitals. So we would then fill this in, and if you don't want to have to count, you can just know that you had all your orbitals full in the beginning. Well, when you mix them back up, they have to be full in the end, don't they? And so it's full. It's 2 electrons in each orbital. But you can count them through. 2, 4, 6, 8, 10, 12, 14, 16 electrons. This is full. Just looking at it, if you realize that's full, that means because you have an equal number of bonding and anti-bonding orbitals, that you had to have a bonding order of 0. You don't actually even have to count them up because there's an equal split. It's half-half. And so full means 0. But you can, if you want. That's 2 bonding here, 4 bonding here, 6, 8 bonding right there. That would be 2, 4, 6, 8 anti-bonding. That's 8 minus 8, and so 0. Anything divided by, or anything dividing 0 or multiplying 0 is, well, 0. And so we don't have to worry about that. All right. So the final thing we have to look at is para versus diamagnetic. And again, well, first off, Ne doesn't even bond. Ne2 doesn't exist. This is all kind of mute and beside the point. But everything's paired up, as you can see. So, P2, this is going to contain your phosphorus atoms from your 3rd row of your periodic table. We do not have to worry about the d orbitals here because they don't have any electrons in them, so we can just ignore that. So let's assume that our diatomic molecules of period 3 elements can be treated in a similar way. that we've used so far, that we don't have to do anything different. And that's a nice assumption because it keeps us from having to do a lot of extra work. And that extra wouldn't actually do us any good. So let's draw this molecular orbital diagram. We can draw this P2 just like it would be N2. Because remember that what makes a group, as in this group nitrogen, then phosphorus under it, which is group 5, is that they have the same number of valence electrons. And so that means that our molecular orbital diagrams are going to end up being the same. And so we go ahead and do that. The only change that we're going to have to make compared to the nitrogen diagram is that we don't have two s orbitals and two p orbitals anymore, do we? Instead, we'll be using 3s and 3p orbitals. So that's a big difference. We turn the 2 into a 3. And there you go. So our 2p molecule is going to end up with 5 electrons from each phosphorus atom, which gives us a total of 10 valence electrons we have to populate. We make our molecular orbital diagram again. Here's our sigma. Sigma antibonding for our s orbitals. And then we have our pi on the bottom, because again, this is in the left side, left half of our p block, just like nitrogen is. And so that would be our pi bonding orbitals for the 3p atomic orbitals. And then we'll have our sigma bonding orbital, and then our pi antibonding orbitals, which are just 2 of them, and our sigma antibonding orbital. Notice that these are always the same. The way I like to always say this is you always put a hat on, and because that looks a bit like a hat, right? See that? All right, now we would then fill this in with our electrons. Notice we can just use the total number of electrons. We don't have to worry about anything else. So we fill this in, the lowest energy one, 1, 2. And then the next one, another 2. And then this one we put up, up, down, down, and we still have 2 more electrons. So the next one we do up and then down, and then we have this filled in. And so now we look at this and we have to count up our number of bonding versus anti-bonding electrons and figure out our bonding order. And so we do 2 bonding electrons down here, 4, 6, 8 bonding electrons, minus 2 anti-bonding electrons right there, and that would give us our 6 electrons that were in excess. And that will be divided by 2, so that bonding order is a bonding order of 3. Notice, by the way, if you want to do this faster, you can ignore this s orbital stuff and just count these. 2, 4, 6, divided by 2, 3. All right, so this molecule right here, di, means everything's paired up, right, together, duo. And so this one is diamagnetic because everything's paired up like so. So which of the following would be paramagnetic? There's sort of 2 ways to do this one. You can either write out the diagrams, or you could have just had the table memorized because you used it so many times, right? And so this would be B2 if you remember back in the boron we did. Otherwise, you'd want to write out your diagram, and that'd be B2. Okay. Which of the following is diamagnetic? So in this case, the easiest way to do this, I would actually start off with the diagram of N2, and then you can just add or subtract electrons from it. So remember, when you have a negative charge, that means you've added a single electron. When you have a positive charge, you've added an electron as well, right? And so what we see here is if you've done the diagrams, you would very easily see that N2 is the only diamagnetic one. Now, having said that, that's sort of the longer way to do this. There is a faster way to do this. And if you know that table pretty well, remember I had mentioned that you might want to go ahead and remember that table. You would have remembered that N2 is diamagnetic, O2 is paramagnetic. Now notice that when you remove an electron, you automatically cannot have them all paired up, can you? Because you don't have an even number of electrons. You can't divide an odd number by 2. That would give you a fraction, right? And so automatically, because we've added 1 electron, we subtracted 1 electron from an even number, that means these are not all paired up automatically. Okay? That is true for all of the diatomics, homonuclear diatomics. Whenever you have added or subtracted a single electron, automatically you don't have an even number of electrons, can't have them, they cannot be diamagnetic, no matter what you had before. So which of the following statements is false? Atoms or molecules with an even number of electrons are diamagnetic. Well, we know that's not true because we had some of the diatomics that are all even, and they weren't diamagnetic, were they? Atoms or molecules with an odd number of electrons are paramagnetic. Well, that actually makes some sense, doesn't it? Let's go ahead and go on to the other ones and discuss that. Paramagnetism cannot be deduced solely from the Lewis structure of a molecule. That's going to take some thinking. Paramagnetic molecules are attracted towards a magnetic field. Well, let's see. The diamagnetics are repulsed. Paramagnetics are parachuting in, right? And so we actually already answered this. I just wanted to talk about the other ones because we already found the false one, right? But one of the things I want to talk about is that I had pointed out the paramagnetic. It has to be paramagnetic. It's odd. It just cannot be paired, right? And the paramagnetism, that you need an orbital diagram, right? You need to see how the electrons are paired in orbitals. The Lewis structure simply does not tell you anything about that. And so, yeah, it cannot be deduced from that. That is true. I know that sometimes be careful when you see these sort of questions because you can have a false of a false. And that's something that's bad English, but good questioning. All right, so heteronuclear diatomic molecules. So the homonuclear diatomic molecules, that was the same nucleus on both sides. Okay, so again, this is going to be where you have different atoms. There is a special case that involves molecules containing atoms adjacent to each other in the periodic table. In this case, the molecular diagram, MO diagram, can be used for the homonuclear molecules as the atoms involved in these molecules are very similar. And so you don't have to really worry too much about the slight difference. Typically, by the way, when you do this, you always do the one with the higher electronegativity would be the one you would pick as the one you take the homonuclear diagram for. So use the molecular orbital model to predict the magnetism and bond order of the NO plus and CN minus ions. Okay, so first off, we're going to do the NO plus ion. This has 10 valence electrons. That's from 5 from nitrogen, 6 from oxygen, and then minus 1 because we have a plus, which means that we've lost an electron. The CN minus ion also has 10 valence electrons in this case, and that means that we have 4 from carbon, 5 from nitrogen, and then we have a negative, which means we've gained an electron. Both of these ions are actually diamagnetic. The bond order for both of these is going to have an 8 minus 2 divided by 2, which will be a 3, which is 6 divided by 2 is 3. And this right here is the diagram. So what we see here is we have essentially taken here something very, very similar to what we see for the nitrogen. And we have then filled this in with our 10 electrons. And we have gotten this right here, which is an okay diagram for both. That actually will be fine. And there we go. By the way, they're isoelectronic, which means they have the same electrons, which is why they are the same everything. Yeah, there's a little trick. So, these energy level diagrams for diatomic molecules, when the two atoms of a diatomic molecule are very different, your energy level diagram for the homonuclear molecules can't be used. You have to start having something much different. And that's because they simply will be so different electronically that it won't even make sense anymore. For example, HF shows you hydrogen fluoride, a very good example of this. So the electron configuration for hydrogen has an s orbital with one electron in it. The electron configuration for fluorine has a 1s, 2s2, and then a 2p5. And so you can't even combine the 1s orbitals because one of them's a valence shell, one's a core, and you end up having to work with one of the p orbitals from fluorine is going to be bonding to the hydrogen because those are what will be able to overlap. So you get a very, very different behavior. So right here we have the example of this orbital energy level diagram for HF. Here we have hydrogen, which again has our 1s orbital with one electron in it. Here we have our fluorine, our unpaired electron, and our 2p orbital. It's the only unpaired electron. It can just directly be used to make this single bond. You will notice, by the way, that the hydrogen is represented higher energy than the fluorine. That's actually pretty accurate because fluorine has such a high electronegativity. It's very, very good at containing these electrons. This is actually showing you that it is very hard to strip this electron off of fluorine. And it is much easier to strip it off hydrogen. Now, in this case, these are going to come together. These right here will be your molecular orbitals. Again, it will be a direct overlap. So we'll have a sigma bonding and sigma antibonding. Notice we don't need anything else. We don't have to worry about anything else. Nothing else is going to be involved in this bonding because that's all we need is a single overlap making a single bond. That's it. Now, these two electrons will go to the lowest energy orbital, which is this sigma bonding orbital. In the case where you have it as an s and a p orbital coming together to make these, you typically don't even bother to label them. It's just not very useful to label these at this point. There we go. So our HF molecule, this should be stable as both the electrons are lower in energy relative to their energy in the free hydrogen and the free fluorine atoms. The electrons are going to be preferred to be closer to the fluorine atom, and that's actually where we get that normal electronegativity bond polarity that we've been discussed before. This electron pair will not be shared equally. This is actually pretty close to an ionic bond, but it is still a polar covalent bond. It is not actually ionic. Fluorine will have a slight excess of negative charge because the electrons will spend more time around the fluorine. The hydrogen will be partially positive because they will spend less time around the hydrogen. This is actually a decent representation of the hydrogen and how often electrons are end up around there versus the fluorine and how often it has electron density around it. You will notice the electron density spends a lot more time around the fluorine. So let's consider the molecular orbital description of the NO- anion. Which of the following statements is false? NO is paramagnetic, NO- is isoelectronic with CO. The bond energy in NO plus is greater than the bond energy in NO minus. The bond order in NO minus is 2. So we're looking for the false one. The ones that say isoelectronic are always probably the easiest ones to check because literally you just have to total up the valence electrons. I would always start with those sort of things because they're extremely easy to check. In this case, we can see that this carbon actually has one electron less than nitrogen. So an NO minus is definitely more electrons than a CO. That's not, no, that's false. So, combining the localized electron NO-MO models. Now, obviously, these two, I describe them as layered on top of each other. And they are. They localized electron and the NMO model are actually a continuous model that is applicable to each other. They do work together. And this sigma bonds in a molecule, these can be described as being localized electrons. And that's because in these sigma bonds, the electrons are between the two atoms. And so they're very, very easy to localize because they're contained. They're nicely contained between the two atoms. They have borders. The pi bonds, however, have to be treated as being delocalized. And that's because when you look at the pi bond, it is above and below the atoms. They don't have nice cutoffs and borders. They are, they can be shared. They can freely flow. They can move around a lot more. They're not nicely identified as being here. Okay? You can't point between the two atoms and go, that's where those electrons are. They're not. They're delocalized. For molecules that require resonance, your localized electron model can be used to describe the sigma bonding. Those localized electrons will be your sigma bonds. The MO model can then be used to describe the pi bonding. And your pi bonding electrons will be your delocalized electrons that are being shared kind of strangely and moving around. Those are those resonances. You always notice, if you look at the resonance structures, the signal, there's always a single bond in all those places. It's the double and triples that are moving around. So for example, here's a great example, benzene. All the atoms in benzene are in the same plane. It's all flat, single plane. The carbon-carbon single bonds, which would be your sigma bonds, are all in the same place all the time. See those? They're all in the exact same place. You always have a sigma bond there because those are localized electrons. These double bonds are actually being shared across the entire molecule. So when you're looking at this, what you really are looking at is this resonance structure describes a singular structure. And that's that these pi bond electrons, the electrons in these pi bonding orbitals, are being shared across the entire molecule. They're freely flowing, they are delocalized, they move around, okay? And so again here, we see our sigma bonding orbitals as described by our hybrid atomic orbital theories. And so right here we see our localized electrons. And we can see it very nicely shows our hybrid orbitals. It has the nice correct geometry. It's a bunch of trigonal planar carbons. See that? And that's why it's all in one plane. That's kind of cool. All right, so the pi orbitals are actually all sticking up, just like we talked about in our localized theory before. These pi orbitals will actually join into a singular series of molecular orbitals that are degenerate, and your electrons can freely move around in there. They don't actually circle like I'm doing, but they pop around in there. And these are known as delocalized electrons, which actually you probably thought they probably look delocalized. You can't point, hey, they're between here. They're not. They're somewhere in this donut looking thing. Okay? And that's delocalized electrons. Excellent. So this is actually why you've probably seen this for your benzene structure. So if you look up benzene, you're probably going to get this picture right here, which is a six-membered ring with a circle in the middle representing that donut delocalized electrons that are the 1.5 bonds. This is actually your delocalized pi bonding being represented. And An interesting side note, if you look at branding for different chemicals and chemical companies, look around you. The more you look around you, the more you will see this structure, though it will oftentimes be cut in half with only half of it showing up or be used as part of a letter in a word. And that's because benzene is incredibly popular with any sort of chemical branding. It's a weird thing. The more you think, the more you look back, the more you'll go, oh yeah, I recognize that. And that's benzene. And again, that's your delocalized bonding. It's been all around you all this time. Excellent. I hope you guys get some use out of this video. Let me know how things are going. Please send me any questions that you have that you don't understand and aren't getting worked through on your book and the OWL. You take care now.